slowly see the slides appearing. So we've got here more than 50 people connected, and I think it's going to increase again to I think slowly get back to the number of the number of attendees we had before. So let's restart, and people will who will just join in the next minutes. Thanks again for attending this second part, the afternoon here. But I can actually wish a good morning for people in America, because it's maybe some of you are waking up. Good afternoon for Europe and Africa, and good evening for Asia and Oceania. But welcome to the second part of the SOFA week, and especially to this symposium. Again, just to sum it up for people that might have joined just recently, we are going to cover different topics of applications of SOFA. We've seen this morning soft robotics. We've seen as well numerical methods, and actually how those numerical methods can be applied on any of your simulations for improving, making it more accurate or faster. And that was often the case to make a application faster. And just before going to the next part that will address medical robotics, I'd like to talk a bit very shortly. So I see still people incoming. Give you some insight and some updates about the community of SOFA. And first of all, I would like to give you updates about really the code of SOFA, what happens in the code of SOFA. You might have seen that in the release and in the release notes that we, and especially Guillaume and Fred, who are working, we are working together on SOFA, but they are the release guys for this development around SOFA. There have been several changes, and I think some of them are already major changes, and that will affect, hopefully in the best and in the good way, for you. First, there have been work from Alex that you might have seen in the commits and so on, passing through on multi-threading, especially multi-threading for collision detection, and on making the free motion parallel, like making in parallel free motion of different objects and the constraint resolution as well. There is another big project ongoing, which is the one from Fred, that is SOFA Next Gen, that will, I think, affect most of you, at least if you have a plugin, it might affect you, but it's for the best. We are cleaning quite extensively the core of SOFA to make it 100% modular, way more modern, and that's thanks the almighty Fred, which is working on the Next Gen project. Third, and that's again Alex, that was on the first point, multi-threading. Alex is working on the redesign of matrix assembly in SOFA. It's gonna ease so much things, ease so much the reading, the extraction of matrices in SOFA. So you cannot, I mean, I guess you can already foresee the potential this kind of project can have, and there will be especially application constraints, again, just like ZQ mentioned this morning. And finally, the SOFA Phoenix coupling that Arnaud presented as well this morning. I think that's really 4 major developments ongoing. There is way more than that, obviously, in each research team, in each company. You have products ongoing with SOFA, so that's there is major evolutions currently going on with SOFA. Stay tuned. I mean, on all the social media, you can follow what's happening in SOFA. But if you are curious, more especially about one of them, never hesitate to let us know. There is projects ongoing, so like European collaboration project, international project, national projects ongoing. Like I'm here citing 3 of them that I know pretty well, but never hesitate to let me know about your own national, European, American, whatever project you have, whatever the size of the project. It's always good for us to actually know about it so that we can connect you to the best partners if you're looking for some. New projects are actually incoming for 2022, and not the less. Actually, there is one which is quite significant for us in Europe here, which is T-Rex, that will be focusing on robotics, and SOFA will be the main software for handling all the soft part in those robotics application, whether the robot is soft or interacting with a soft environment. And some US grants as well are currently being applied, and I'm obviously forgetting some. I just specified those things yesterday evening, so I'm obviously forgetting some of the project. But again, never hesitate to provide us feedback about your projects when they got submitted. We can always help, and also accepted. It's even better. Continuous integration and continuous development and the different tools around that, that's a major work done by Guillaume, which is again with me on stage. So there is major changes here on using SOFA with a Docker container. Arno mentioned that for Phoenix earlier. We have the same with Sofa. And GitHub Action, that's definitely the latest news from Guillaume. There, here you will be able, for your own plugin, to set up all the GitHub Actions to make the testing and the continuous integration of your plugin safer, more robust, and automatic. Last and not least, there is new plugins incoming. You might have noticed, obviously, already at the last technical committee, there was the release of the Sofa Python 3. Now, Sofa Python 3 is fully maintained, is fully used actually also by the community, and the last plugins are making the migration. So never hesitate to get into the Sofa Python 3 plugin. We would be happy to help. Caribou, it has been mentioned before, and we'll talk again about it later on. And more recently, Beam Adapter, it has been mentioned in various presentations already today, which has been open. All those plugins are open sourcely now available, and that's for the latest one, Beam Adapter, the latest news since it has been released last Friday. So if you want to go for beam simulation using the Timoshenko beam theory, rod theory, just go for it, take the plugin. We cleaned it as much as possible. We added examples as much as possible, and hopefully soon we will add also some docs on it. If you need, we have already some available documentation for that. So those are just a very short insight of what is going on around the technical all the technical aspects of Sofa. If you want to know more, it was just a teaser, but if you want to know more about one of those or more projects, just meet us tomorrow. It's going to be again online. There, you might have already received the link, and that's going to be the Sofa Technical Committee, and it's actually the 12th edition. Now, a word about, for those who are just coming closer to Sofa and just starting with Sofa maybe, I just wanted to stress again the different entry points that you can have in the community. First, for those who are struggling installing Sofa, if there is still some people struggling, but it might happen anyway if you are using plugins and so on. Struggling installing Sofa, struggling using Sofa or a plugin, there is one place for you, the forum. You can definitely go on the forum, ask the question you want. I mean, we try to be as responsive as possible. Unfortunately, this summer and also these last weeks here, with the organization of the Sofa Week, responsiveness decreased significantly, and we apologize for that. We'll be back on track soon. Second, if you're struggling with the Sofa API while developing or interested in just chit-chatting with the developers, really on the developer standpoint, just join us on a Gitter chat. We have a Gitter chat. The link is here in very small, but we'll add it in the chat. Join us. Just come chit-chat and make yourself known and discuss with the developers, as Arno did that earlier. I mean, in the last weeks, we had as well Juan Jose from Spain that was also doing that earlier. So the more developers we get, I think the best the developers are getting. Thanks, Guillaume, for copy pasting the link. You can directly go on the Gitter, and you'll see there is basically every one of us. But that's for development topics that you can go there. And finally, if you are noticing a bug in Sofa, like really you know that it is a bug, you identified a bug, even if you're not sure yet from where it is coming, but you do know that it's a bug, never hesitate to go on GitHub, create what is called an issue, or if you are improving the code and not like you noticed a bug and you are fixing it, improving it, you can actually contribute, making what is called a pull request and improving Sofa on an everyday basis. Just so that you know, there's one thing here in the slide that might evolve, and let's say that we can promise you that for hopefully January. That's what we are aiming at. It's for the forum. You might have noticed that the forum is a quite old-fashioned forum, sometimes a bit struggling with registering or posting questions or getting, most importantly, responsiveness from the developers here. We will make this forum evolve, and most probably we're going to use the GitHub discussions feature that is basically a Stack Overflow-like chat. Yeah. Finally, all those you can get on the Get Involved page. But I just wanted to really stress that again, to let you know, basically, never stay alone if you struggle, never stay alone if you have a question, never stay alone if you are having a project or a contribution or a new plugin. Let us know. That's basically our work to help you and to assist you in that. About the community, you might have noticed that there is actually more and more users, more and more developers that are actually involved around the project. We've been creating, there have been the last 10 years, 7 companies. This number is actually now stable for at least 1 or 2 years. But there is at least, and I wrote that somewhere on my notes, but there was at least, I counted 5 different ongoing startup projects. There were actually 3 in France, 1 in the US, and 1 in South Korea. So you see, there is still, I mean, just a proof that the LGPL license is really fostering this kind of spin-off creations. And let us know about those kind of spin-off, because our role at the SOFA Consortium is to assist you in any way we can. I mean, promoting, finding the good partners, finding the good profiles as well to recruit. That's something which is important. So that's good news for us. Again, a project of startup creations. One point I would like to stress, and that's the point of this slide, it's maybe, as you can notice, there is quite a strong and a huge difference between the number of, I would say, release developers against the everyday developers. Never hesitate to contribute to SOFA. There is no one here is here to judge the quality of your code and so on. We're going to analyze that, review the code, and help you improving it if it needs improvement. But never think that your code is not good enough to get in SOFA. Okay, never. Just we prefer a very dirty pull request than no pull request at all. We would always be here actually to help you clean the code. That's why we created this consortium, so-called consortium. Our role is to gather as many people, build a community. We take care about the maintenance, industrialization. That's actually the great work of Guillaume. Coordinating the development, making sure that people are actually not developing twice the same things, and also that's another stuff that Guillaume is doing. It's and now with Fred, reviewing all the pull requests, all the contributions, and thanks to all the latest contributors of the release. Animation and support, that comes with events and forum, and the growth of the ecosystem. So again, if you are having any kind of project collaboration, startups or whatever, let us know. We are acting as a third party, and we are only here to help. Last year, we are getting more and more engineers. Actually, one more that was Fred, dedicated on SOFA. And there is actually, we could even get more, but for that, that's just a question of criterion, and that's the criterion given by INRIA to give us actually and to commit more and more developers to the SOFA project. For that, the more consortium members, means partners supporting SOFA that are using SOFA up to a point that they decide to actually support us. It's actually can be a lot of it can be an amount of money which is not neglectable for a research institute, but still, I mean, it's up to 5,000 euros for technical memberships, but it's helping us a lot, because it allows us, the more members we're going to have, the more engineers we're going to get dedicated to SOFA. We had last year the Krewcun National University and the University of Florida, but both actually, since they're academic partners, cannot always pay for that. But we are super happy this year to announce that we're going to have Insimo, which is a former spin-off company from SOFA, supporting officially SOFA financially, and that's they're going to help us and work with us in the building of the roadmap, technical roadmap, along with the Fraunhofer and Hassan Medical Center tomorrow along the technical committee. So, and I won't tease, but there should be more early 2022. So hopefully more members. But again, as soon as you can support us, just if you can do it, it means that we're going to have more and more developers. It's not like we are doing anything from your money, but just investing it 100% on SOFA. If you cannot pay for SOFA, there is another, and that's maybe the second and most important point, it's contributions. Just contribute any way you can, doc, tutorials, bug fixes, plugins, whatever. And that's the purpose of the SOFA Awards, also to really reward people that are contributing the most to SOFA. And again, I would like really to thank first all the institutions below that are actually contributing to SOFA and the developers. Use and cite SOFA, obviously, in your papers. That would be nice, and really take part to any project discussions like in the technical committee around SOFA. Just to know that donations are also possible. Now, for you, maybe whether you are a student or someone managing a team, research or an industrial team, we can also be useful to you. in various purposes, especially recruitment or finding a new job. For instance, right now there will be Eleonora speaking later on that is actually soon finishing her PhD. I think Arno is also close to the end of the PhD. So we have very, very good profiles that soon going to end their PhDs. I'm mentioning 2 of them, but actually we have way more than that. So if you're interested to know who is available or whatever, just still 1 year for Arno. So just be patient, a bit more patient for Arno, but it's going to be mid-2022 for Eleonora, and there is other profiles that are coming up in the community. So just let us know if you're looking for a job. Let us know if you are looking for someone, and use as much as you want the LinkedIn page. It's made for that, so you can yourself poke us, post things or whatever. Never hesitate as well to collaborate with independent developers and development companies. Erik, who is among us today from the Infinitec 3D company, is going to present his latest work around SOFA, and I think you won't be disappointed. That's thanks, Guillaume, for the time's up. I'm actually almost. I need just a few minutes if I can just present the awards and the contributors. So it was my last slide about the consortium messages, and I'm gonna, if it's okay, take 5 minutes, just 5 minutes for presenting the awards. So just contribute the way you want, and what is important is really appropriate yourself and never stay alone. Stay in contact with us as much as you can. Well, we have as every year an award competition. So there is 2 prizes: an organizer's prize and a public prize. The organizer's prize has already been defined by an organization committee. You see, there is actually quite a diversity here of people. If you want to be next year among this committee, just let me know. It's completely open. So thanks to Nazim, Frédéric, and François Damien, we're going to have a winner for this organizer's prize. Thanks a lot for taking the time, guys. And that was the criteria: readiness level, impact, documentation, installation, usability, and something that we always want to push forward is external contributors. So guys, never hesitate to contribute. You can always elect, and we'll put again the link in the chat, elect the public prize. There is 4 different candidates, and I will do that quite quickly. Sorry guys for making that short. So first, Peter, who is proposing a QSOFA GL viewer tools here. So it's based on PyQt. So you can definitely go directly on the GitHub page for that, and you can even test it yourself. Second, there is a proposal of a new force field in SOFA called so based on the Reisner-Midlin model. So that's proposed by Nan. So it's for shell elements. It means deformation in plane, and there will, I think, soon also be out of plane. So model for thin but 3D elements like plates here. So that's a slide. I'm sorry, Nan. I'm going a bit faster just to avoid spending too much time, taking too much time for the next speakers. And finally, third, SOFA benchmark. So coupling SOFA and Google benchmark. That's Alexandre who proposed this new actually project around SOFA that could be used by anyone to test, measure the duration of execution of snippets of code. So it's very similar to unit test as it is written. Last but not least, and it has already been presented by a bit Arno and others in their presentation, Caribou and SOFA Caribou, which is an entire plugin allowing to rewrite and reformulate the way we are computing continuum mechanics in SOFA, separating the mechanical model, separating the integration, the ghost points the number of ghost points, for instance, and the type of elements. You'll have the full description online on the award page. So do not hesitate to go there, vote for them, for the one you prefer, and we'll give you the winner of the public prize at the end of the day. So for this afternoon, and I'll be quick here, we'll have 3 sessions: medical robotics, medical simulation, and 2 parts: haptics, VR, AR, and training and planning. Again, breakout rooms for discussions, and we're going to directly start with you, Stefan, if it's fine for you and if you're ready to share your screen. So we're going to have the presentation of a soft robot that's going to be used as a phantom of a prostate. So I hope, sorry for being too long, guys, and do not hesitate to add in the chat if there was a question.
right, so I hope that everybody can see my screen.
Perfectly fine, thanks.
Yes, good, great. Yeah, so thanks, Hugo. Yes, so I want to talk today about the topic of model-based sensing for the implementation of a smart prostate phantom. So in the team and in the recent years, I've been working here in the Frost in Realil. I've been exploring the idea of intrinsic sensing for deformable devices. And since we're using, so far we follow a model-based sensing approach, and particularly it's about using inverse problem solving to find the forces that best explain the observed sensor values. And the first devices we developed were soft silicon pads with embedded cavities, so air chambers in them. So here on the lower left, you will see two examples: a rectangular soft pad and a kidney-shaped soft pad. And inside there's these air chambers. And as you can see, that if there's an external force being applied to the device, there will be a deformation of the cavity, and this will be measured as changes in volume through some sensing systems, which could be airflow sensing or pressure sensing. Overall, what we're interested in is in reconstructing the forces and also the resulting shape. And yeah, so the potential applications we see for this is medical phantoms. So we think about them as being anatomical soft robots. So just a quick view of what these previous results. So you can see here that I'm interacting with the pad, pushing on it, and the force and deformation are estimated. So that was back in 2019. And so since towards the end of the last year, I was working on this COBRA project, and this project is about cooperative brachytherapy taking place at the University of Lille and with some partners in France, England, and the Netherlands. And the idea is to automate adaptive brachytherapy for the prostate. So brachytherapy, what it is a treatment for prostate cancer, and for that, radioactive seeds are deposited near the tumorous regions to destroy this tumorous tissue. And imaging techniques such as ultrasound or MRI are essential to supervise the organ motion and the deformation for correct seed placement. So here's the intervention as it is performed classically by a urologist. So he's inserting needles carrying the radioactive seeds to the target locations. And an imaging device, in this case the ultrasound probe, is in place to supervise the organ motion and also verifying that the needle trajectory is the correct one. So the idea is to completely automate this procedure, so will be a robot that will perform this procedure. Excuse me. And to study and evaluate this automated and adaptive intervention, we propose a phantom. So this phantom has sensing and actuation capabilities. So it is based on the soft robotics technology we have developed so far. And so here on the left, you see that there's already a robot platform able to steer a needle. In this case, we have a biopsy needle. And then on the top, you see the proposed device, which is the prostate phantom. And on the right, you see how this phantom is represented in simulation and so forth. And this work has been recently published in a journal. So how did we design the phantom? So on the one hand, we have the organ itself. So this is the prostate bulb, and it is attached or suspended by 4 arms that have accordion shape. And in these arms, we have embedded cavities. And by using pressure sensors, we measure the change in pressure inside these cavities when there's an external force acting on the phantom. So in this scenario, we see here that there will be a needle acting on a particular point, the P external. And when we do so, there will be particular distributions of the pressure. So in this example on the right, you see that I'm pushing on the phantom in a downward fashion. So the phantom is on the one hand moving forward. So you see the pressure increasing due in the frontal sensors, as well as in the lower one, whereas the upper one, corresponding to the magenta color, is being stretched, and therefore we see decrease in pressure. So the idea is that these signals are related to the force magnitudes we want to establish. And we use this particular sensor, which is quite sensitive and has some interesting properties which allow us to make this device MRI compatible. And as I just explained, these arms are in place to allow the sensing of the external force. So we've to obtain signals related to the external force. But they also, the arms are a lumped representation of the elastic attachment of the prostate to the surrounding tissue and organs. So basically, we're emulating the mechanical properties of the surrounding elements inside the human body with these arms. So the choice of size, angle of attachment, the material, and so on will determine the stiffness of the, or not of the organ itself, but in how it's going to move. And so they are important design parameters. So this is something we need to work on to find appropriate values that are anatomically correct. In this particular study, we are concentrated on to achieving clinically plausible motions, meaning that the range of motion we observe is coherent with what is known from clinical data. And what is interesting is that using this particular pressure sensor, which is very sensitive, allows us to employ very long tubing. And so that means that, so in this case, we have 12 meters. We can remove all the electronics from the proximity of the device, and therefore we can remove them from MRI influence. And so this device becomes MRI safe. So the idea is that if we want to use MRI imaging with the robot, so both the robot and the device need to be MRI safe. So coming back to how this is implemented in SOFA, we have for each time step the internal elastic forces of our device, which is a linearization of the previous time steps. So we have the stiffness matrix, which is computed in the beginning of the simulation, is propagated for each new time step. And if we consider the quasi-static regime, we have also additionally some known forces such as gravity. Here's the internal elastic forces, but also this constraint-based modeling. So we have a vector of external forces and a Jacobian or node selection matrix, which maps these forces to nodes on the FEM mesh. And how we can leverage this to find the force load is that we need to establish the relationship between the change in force and the change in volume. And so, as I mentioned previously, we have the force variables that are mapped through H to the particular nodes on the FEM mesh. The compliance matrix will transform the forces into node displacements, and then by using the partial derivative of the volume function, we obtain the changes in volume. So for this recipe, we need phi, which is the function that determines the cavity volume for a particular configuration of the FEM nodes, and the derivative will give, with respect to the node position, will give us the change in volume. So this is done for one cavity, and we can summarize this relationship for all cavities. So we in the matrix W, which relates the forces to the volume. And so what we need to do to solve this is to formulate it as an optimization problem. So meaning to find which are the forces that minimize the differences between the simulated change in volume and the real change in volume. So this is what we obtain from our real world measurements from the pressure sensors. So using the ideal gas law, and the output is that we get some forces. So going back to this topic of the clinically plausible motions,
just so that you know, you're at the end of the time, so there is. I mean, we have these 5 minutes of questions time, but you can exceed it a bit to conclude.
Yes. Thank you. So I think I have to hurry up. So, but of course I'm available for discussion later. So yeah, just to say that from clinical studies we get some ideas about the motions, rotational motions, but also translational motions, particularly in the direction of insertion, but basically some lateral and upside and downside motion. And so what we did perform some perforation tests. As you can see here, we inserted this biopsy needle, and basically by using optical tracking, we are tracking the position of these optical markers so that we get a ground truth state of the deformed prostate or the moving prostate, and we have the same points in simulation, so we can compare the two values. And so yeah, in these terms, we're quite happy with the outcome. So we see that the correlation between the ground truth and the estimated by so far, the correlation is quite high, even though there's still some remaining errors. But so the dotted lines are the estimation so far, and the continuous line is the object ground truth values. So in this particular experiment, the following is quite accurate. There's also some experiment regarding the eye handheld tool. So here it's more dynamic kind of interaction, just to kind of test the more the limits of the device. And so in this case we obtain also a good following of the trajectory of the real prostate motion, but we do still have to investigate why sometimes there are major or some deviations which are not always systematic. So we still have a lot of work to do to understand where this behavior is coming from, but in general we are quite satisfied with the accuracy. So in the future we hope to get some patient-specific anatomy for our phantoms, different materials, handle this in simulation, maybe model this needle interaction in a more complex way, and generate synthetic imaging. So yeah, thank you for your attention, and I don't know if there's more time for questions, but at least we can discuss in the breakout sessions.
Let's take at least one question. Is there any question in the audience? So first, thanks a lot for the very nice presentation and the very nice videos as well of your the prostate phantom. I put also the link for a paper to a paper in the chat for people that want to read a bit more. And again, there is time for a question. Otherwise, I'm gonna. Paul is asking if I'm right. You find the contact position only using the forces on the sensors. Is the localization precision the same around all the prostate?
Yeah, so that's a good point actually, but it's not the case that we're detecting the interaction, the point of interaction. So we're only estimating the magnitude, but the point itself is fixed. So the key here is that we are estimating 3 degrees of freedom of the force, and we have force for pressure values. So actually estimating the position from these values would probably be difficult. Maybe not impossible, but what I consider to be more practical would be to use another sensing system. So if this is a phantom, we can suspend it in a cage, and maybe use some optical put some cameras in to detect the contact location and so on. So basically get an external feed for the contact location.
So Paul is continuing the questions, and so he was asking some more. But so Paul, I'll ask you to keep again further questions for the breakout rooms. Thanks a lot, Stefan, for the nice presentation. Yeah. I think the synthetic data creation that you mentioned as a conclusion is really interesting. You know, to use that kind of phantom for generating data, then those data being used for maybe training, as we have that a lot. So yeah, very interesting. Thanks a lot.
Yeah,
and see you in room 1 for the breakout room. Martina, are you available for the second presentation?
Yes. Can you hear me?
Yeah, perfect. You can, I think, go ahead for sharing your screen.
Yes. Okay. Can you see my screen?
Perfectly, yeah. So, the presentation is full screen. You can go ahead. Thanks.
Okay. So, hi everyone. I'm Martina Finocchiaro. For those of you who doesn't know me, I'm a Marie Curie PhD student between 2 universities. One is Università Politecnica de Catalunya, which is where I'm now, and the other one is Scuola Superiore Sant'Anna. In this small talk, I will show you the role that plays simulation and SOFA in particular in my PhD research project, which is about understanding what is the optimal solution for human-machine interfaces in robot-assisted intraluminal procedures. To give you a bit of context, the Marie Curie project that I'm part of is called ATLAS, which stands for Autonomous Intraluminal Surgery. We are 15 PhD students around 7 universities in Europe, and what we do basically is, let's say, developing robotic devices for intraluminal procedures. Here you can see a demo of one of the devices that we are working at. What are the intraluminal procedures? Well, are all those kind of medical procedures that are conducted inside body lumens throughout a natural sphincter. The body lumen could be like the urinary tract, the blood vessels, or the gastrointestinal tract. In case of robotic intraluminal procedures, the device that we use to steer inside the lumens are like snake-like robots or endoscopic capsules, such the one you can see here in the demo on the right. This is called Endovespa, and this is a capsule for robotic colonoscopy. It is steered through a magnetic link. So an external magnet is moved by the user and allows to move the capsule inside the colon. Well, intraluminal procedures are really useful, and because and they are really popular, of course, nowadays because they are minimally invasive. However, they are really complex to learn and to master for the clinicians. And in the last decades, many devices have been developed, and many human-machine interfaces have been developed to control intraluminal robotic devices. However, there is a lack of knowledge about what is the optimal solution, meaning what is the optimal human-machine interface that minimizes the cognitive load and the physical load of the users and maximize the quality and safety of the procedures. This is my research question, and here we come to our question, that is, what is the role of simulation in all of this? Well, the idea is to create a simulation environment for the intraluminal procedure, which in my case is colonoscopy, that should be open and shareable, modular, scalable, and realistic in terms of timings, mechanical and visual rendering. Then implement different human-machine interfaces in these in this simulated environment. As human-machine interface, I mean different physical interfaces such as a joystick or haptic device to drive our capsule or our robot inside the simulated environment, different control strategies, and different assistive tools to the users. Then generate some tests with clinicians, comparing the different human-machine interface, and extract data in order to evaluate the procedure, so to evaluate the performance of the user and understand what is the optimal solution. To do so, SOFA represents a really good opportunity because it gives me the possibility to create an open environment in which simulated environment that is realistic enough to make the users feel as they are performing the procedures in a real case. And it's open, so it allows me to connect different devices, implement different control schemas, and also allows me to get all the data that I want then to evaluate the performance and the procedures, and to replay also the simulations if needed to get even more data. how to create the environment. So in my case, as I said, I wanted to develop colonoscopy. So I started from CT colonographies from real patients, 3D reconstructed the colons, applied different volumetric and superficial mesh for the different models of the simulation, and then applied a nice texture, like a realistic visual texture. Then used the SOFA simulation, of course, for simulating the environment, and the SOFA Unity plugin from Erik Pernod in order to have a more realistic visual rendering. Here you can see a demo of a user that is steering a capsule like the one I showed you in the previous video inside the colon. So the idea of colonoscopy is that in the endoscope we have a camera, the tooltip, and we use this camera to visualize the internal mucosa, so the internal walls of the colon, in order to check for any lesions. We also implemented the deformation, so we gave a mechanical model with deformation after the contact between the capsule and the internal walls. So here you can see on the left side the internal view, so the view from the camera, the tooltip, and on the right we can see the deformation of the colon after the collision on the top right here. So what's next? The idea now is to improve the biomechanical realism of the platform, so add some movement to the colon. We want to add peristalsis, which are some contractions, natural contractions, waves-like contraction that travels throughout the whole colon, actually to all the intestine, and allows to push the food in during digestion. And we have these also in colonoscopy. And also to add air insufflation. So now, as you saw in the video, the colon is open, no? So the lumen is opening, in the visibility is really good. But actually, in reality, the colon is collapsed. So you have to open it up, and you can do it by insufflating air. So we need to implement this. I'm at the end of the talk, and I leave you with a small video of a user, so of clinicians from Ospedale Le Molinette of Torino, that is testing the platform using the joystick. I thank you for your attention, and super thanks also to Hugo, to the organizer. I'm happy to take any questions and comments, of course.
Thanks a lot, Martina. Thanks a lot for the nice presentation, and I got already several people saying, oh, that they enjoy sometimes understanding, fully the presentation, when there is sometimes for some of them not too much math in it or so on. And here it's a nice rendering and a nice use of SOFA. Is there any questions? So I see already one, but if there is any other question than the one from Sergei, please post it or unmute yourself, and do not hesitate to take the mic as well. I'll tell you the question of Sergei, which is first, thanks for the nice presentation, and how have you how have you selected the mechanical parameters for the simulation? That's the question of Sergei.
Okay, so I derived the mechanical parameters from some articles in the literature in which they did tensile stress on actually animal tissues, so from colon tissues coming from pigs, I think. And I derived from there the young modulus, and then implemented using actually here the one that you see here is a linear model of deformation.
All right, I'm gonna I think give you a bit of insight of who, where does the question from Sergei come from? Sergei also worked a lot during his PhD, because he recently got his thesis accepted, so he's now a doctor as well. He worked on data assimilation, especially using Kalman filters, which are Bayesian inference-based methods for evaluating what would be the properties of some tissues based on measurements that you would do. And he made a specific plugin for that that is called the Optimus plugin. So basically you have a model, and you have some parameters that you are actually not certain of, or you're not certain about the values of those parameters. And using some, for instance, input surgical data, you could actually optimize the parameters. Just so that you know. So I added in the chat the link, you could have a look later on. And there is a question of Christian, so I will let Christian, sorry, I did not see the hand reader, so please go ahead, Christian.
Just a small question about the, because if I understand well, you use this simulation to choose your interface, right?
Yes.
To drive the robot. And do you have some, do you know what I didn't really get what device do you plan to use? Do you plan to develop your own device, or do you want just to test some existing device?
Well, the idea is to create a platform in which then you can test whatever you want, but until now we just tested commercial input devices such as joysticks of different kinds and haptic device. Yes.
And you have I don't know, do you have because one of the difficulty, if I understand well, the difficulty is probably to drive the drive the robot inside the sorry, inside the vessels. Not vessels. Sorry.
The column.
The column. So thank you. And do you does the surgeon has fully control of the robot, or is it completely teleoperation, or like you predefine a trajectory to avoid any collision with the walls?
No, at this point they are fully. They can fully control the robot, so they are not. We didn't implement any constraints of that. The idea is that also you can implement them if you want to test if this makes sense or not. So in this case, going back to the thing of having an open platform in which you can implement different things. At the moment, they were fully in charge of controlling the device.
Okay.
Yeah.
Thank you very much.
Thank you for the question. Also, thanks to Sergey for the question.
Thanks, Martina. Okay, computer. Okay, so it was indeed. So there is a comment about the question of Sergey. I will let you read it. Anyway, I will also post some questions, I think, in the chat later on. Thanks a lot again, Martina, for the presentation, for the work you're doing. It's good also for us to get updates of what you're doing currently, and thanks for posting things on Twitter, LinkedIn, and so on, as you as well always do. Thanks a lot. Now we'll have the presentation of Eleonora. So it's really the Italian task force currently working on a framework for autonomous surgery, and she will present us the role of simulation in that. And I was mentioning Eleonora earlier as well as a PhD student that would soon be done with her research work. So again, if you are interested in interesting PhD profiles, you feel free to contact her anytime, or contact us if you want to have a direct contact. Eleonora, are you available for sharing the screen?
Yeah, sure.
Yeah, perfect. We are 4 minutes after the schedule, but it's almost perfect. So it was my fault. I'm sorry. Perfect. We can see and hear you, so it's perfect.
Okay, perfect.
I'll let you the floor.
Okay. Thanks, Hugo, for the introduction. So hi, everyone. I'm Eleonora Tagliabue, a PhD student from University of Verona. And in my presentation, I will talk about our recent work on a framework for autonomous surgery, focusing on the role of simulation. So just to start with a bit of context, nowadays robotic surgery represents the standard of care in many different surgical procedures. Current surgical robotic systems are generally teleoperated by the surgeon from a remote console, as you can see from the picture, for example, the Da Vinci surgical system. However, a surgical intervention is composed of a series of standard elementary tasks, like, for example, tissue retraction that you can see in the video, dissection, suturing, and if these tasks can be automated, they can help to reduce both the physical and cognitive load of the surgeon, who can just focus on the most critical parts of the intervention. So the main challenge when trying to automate a surgical task is given by the working environment, which is first, highly deformable, and second, uncertain. So even though a patient-specific deformable model can be created starting from the preoperative data, the model parameters are generally very difficult to know and can only be roughly initialized in a preoperative phase. So in order to cope with such a complex environment, the autonomous robotic surgical system must have deliberative capabilities. This means that the autonomous system has to continuously monitor the environment with sensors during the task execution. And it must be able to reason and plan a new strategy in case the expected behavior from a model that the system has of the environment does not match the reality. And furthermore, the system has to learn from what it observes and adapt its prior model. So we have proposed a deliberative framework for robot-assisted surgery that integrates the required feature. And in particular, we propose to follow this workflow in order to achieve surgical task automation. So we start from preoperative data that are used to create a physics-based model of the environment, which is used in turn to initialize a patient-specific simulation. Then the preoperative data, together with expert knowledge about the task, are used to generate in a preoperative phase a patient-specific plan of the task. Once the plan is ready, then this plan is executed both on the real environment and on the simulated environment. And the two environments are continuously monitored with sensors so that it's possible to understand if there is discrepancy between what is happening in the two environments. And if there is mismatch between these two environments, we can trigger some specific interventions or adjustments in the task plan in order to improve safety. For example, we can reduce motion velocity. Or we can also trigger a learning module that is able to update the parameterization of the physics-based model, because this mismatch between the two environments might be due to incorrect initial parameterization. So we have tested this workflow that I've just detailed on the automation of tissue retraction, which is a surgical task where we have to manipulate the soft tissues in order to expose a hidden region of interest. So the simulated environment is initialized with the information about the target, which is our region of interest, and an estimate of the location of the attachment points, which represent the simulation boundary conditions. The experimental setup that we have considered is, it's a tissue retraction task on a silicone phantom executed with the Da Vinci research kit. And we have a RealSense camera placed above the tissue that captures the tissue point cloud, and then the surgical endoscopic camera, which allows to understand if the region of interest is exposed. Here on the right, you can see the corresponding scenario in simulation, which is used both in the preoperative phase to generate the patient-specific plan and intraoperatively to monitor the tissue state. I will now talk a bit about the different modules and describe how we implemented the different functionalities for each module. So starting with the task planning module, the task planning module is a module where the expert knowledge about the task and all the possible actions are encoded. And to do it, we rely on a logic-based task planner that is based on answer set programming. The reliance on logic guarantees interpretability of the plan, which means that the plan is generated in plain English, and in this way it can be easily understood by a human supervisor, which is a required feature to ensure safety. Then, in order to accomplish the task, our task planner implements two different kinds of actions: the pulling of the tissue vertically and the folding horizontally when the mechanical solicitation is very high. Then we have a sensing module that continuously receives the state of the robot and the state of the environment. The state of the environment includes the information about the forces that are exerted on the tissue, which are estimated from the simulation environment due to the fact that current clinical surgical robotic system lack of force information. Then we have the acting module, which instead provides the appropriate motion law for each action in the plan. After these modules, we have the monitoring modules that continuously receives the data from the sensor in order to estimate how well the simulated environment, which again represents the knowledge that the system has about the environment, is following the real actual scene. So in order to do so, this module computes a monitoring metric which measures the distance between the simulated and the real tissue state. And based on the value of this metric, the system is classified in 3 different possible warning states. And depending on the warning state in which the system is, we trigger specific actions or interventions. And in particular, when the mismatch between the 2 environments is very high, it is possible that it is due to inaccurate parameterization of the simulation. And in this case, we trigger the learning module to update the parameters. In this work, in particular, we have focused on the update of the attachment points, since previous work have demonstrated that the attachment points are very difficult to be initialized preoperatively and can be estimated only during the interaction with the tissues. Updating the attachment points in the tissue retraction task will not only allow us to improve the simulation accuracy, but also to update the knowledge of the regions that we should avoid during the task. And for this update, we rely on a convolutional neural network, which is called BANET, that provides this updated estimate of the attachment points starting from the intraoperative point cloud. Okay, so we have performed some experiments to assess the capability of the framework to handle situations when, where we started from inaccurate parameterization of the preoperative model. And in particular, we have considered different real scenarios with different configurations of attachment points. And for each of those, we have considered preoperative models with fewer or more attachment points than the corresponding real environment. As a result, I'll just show you qualitative results with this video, where we can see an example execution, where we so the simulated environment that you can see on the right represents our preoperative knowledge, and in this case, the attachment points are overestimated with respect to the real ones. So initially, we go and grasp at the optimal point that was provided by the preoperative plan. But then as soon as the mismatch between the 2 environments is detected by the monitoring module, the update of parameters is triggered, replanning is triggered. So we change the grasping point and we estimate a new optimal grasping point. We start pulling until the maximum 8 is reached. And then once the maximum 8 is reached, we fold the tissue horizontally towards the center until the region of interest is exposed. Okay, so to sum up, we have shown that deliberative functionalities are necessary to automate a surgical task in the deformable anatomical environment. And the framework that I have presented is able to accomplish the task, the tissue retraction task, even when the parameterization of the simulation was imprecise. So in future works, we will start by improving the robustness of the monitoring module, which is at the moment highly influenced by sensor noise and calibration errors. And we will try to generalize the framework also on more complex tasks, including also some learning from demonstrations methods. And this concludes my talk. So we are always looking for potential collaborations, and thanks for the attention.
Thanks a lot, Eleonora, for the nice presentation. There is already a question of Stefan in the chat that I'll give you, but it's quite cool to see really the full the full pipeline of of an application. So you can keep the presentation, or I'll tell you the questions, and if you don't get with my English, I'll let you check out the chat.
Okay.
So how long does it take to estimate the parameters and replan when there is a mismatch identified?
So
it's a great talk, Stefan just said.
Thanks, Stefan. So thanks for the question. So actually, we have tested the framework, and it is able. So it is totally compatible with the intraoperative time constraints. Actually, we have a paper that we just presented last week at the ISMR Symposium, where we estimate the planning and replanning times. So maybe I'll put the link on the chat so that you can check it out. But the time is in the order of seconds. So for the estimate of parameters, like the method for the update of the parameters takes just few milliseconds because it's based on a neural network. While the replanning, we have found that it actually depends on the dimension of the search space for the selection of the new grasping point. So that's the more burdensome part.
Thanks a lot for the reply. And I would say misforwarded the message. It was great talk as always. Is there any other question for Eleonora? Just giving the time a bit to the audience. So I'll take one because that's something we never discussed that topic. It's about the computer vision aspects, like you have cameras and so on. So here again you have your own platform for gathering the points. I guess it's a point cloud that you're getting and then matching them to the simulation. Do you have that yourself as well?
Yes, definitely.
Okay.
So in the real environment, we are using the RealSense camera at the moment, and the endoscope as well. So for this, it was a preliminary experiment where we used both these sensors, but we would like to move to like stereoscopic cameras. It is more clinically realistic setup in the next.
Right. I think there again there would be a plugin existing. If I'm correct, there is one called SOFA CV for computer vision, because it's coupling actually SOFA and OpenCV. So there is several work that already exist around computer vision. So if you need anything, or at least want to check what has been done so far, do not hesitate. I think also there is work ongoing at Mimesis and also at DeForest on those topic of computer vision. Since you are, thanks again, Eleonora, and since the audience is too shy for the moment, and I'm sure there will be people in the breakout rooms for asking questions, I'm just taking the opportunity to move to the last, and then we'll have plenty of time, so 20 minutes of discussion time, to Camille, that will present us his work now not anymore in Clermont, but in Lille, working on plastic Cosserat beams. And the different kind of applications you'll see will move from the belly to the ears. The floor is yours, Camille. You should, perfect.
Thanks. Thanks for the intro. Can you hear me well?
Yeah, we can hear you well. We see your screen for the moment, and I'll let you know as soon as you go full screen. But
okay, that should be it.
Perfect. Yeah.
Okay. Thanks.
Go ahead.
Thanks. So as Hugo said, I'm Camille Krewcun, and I'm a postdoc at the DeForest team at INRIA Lille, so in the north of France. I'm also, like my postdoctoral work is also funded by the same Cardiotest project, which I'm going to mention a bit later in this presentation. And I'm going to talk about an extension of the Cosserat beam model to plastic mechanical behaviors, and I'm going to illustrate that with some applications. So first, this work is based on the discrete Cosserat model, which you might already be familiar with, which basically we use in SOFA to represent beam elements. So it's similar to the Timoshenko beam model, but you have high, let's say, specificities differences between the two. Mainly in the beam Cosserat model, we have a strong assumption that each beam element has a constant strain inside the material. And the second difference is that whereas in the classic Timoshenko beam representation, the degrees of freedom of the beams are position and orientations, here in the discrete Cosserat model, we describe each beam segment with 3 degrees of freedom of strain directly. And so it's limited to angular strain in the model I'm speaking of. And that means torsion, bending in the Z direction, and bending in the Y direction. And basically in the model, you have the ability to recursively find the position and velocities of your model, so classic degrees of freedom, from the strain degrees of freedom we have on each element. So I'm going to go a bit fast on this because it's not the main thing I'm going to talk about. You can find this model, the discrete Cosserat model, in the Cosserat plugin, which is open source and which has mostly been implemented by INUSA. And in this plugin, initially, the mechanical behavior of the beam elements was purely elastic, meaning that, as you can see here, you had a linear relation between internal forces and so the strain degrees of freedom. And in the past few months, what we did was extend this behavior to plastic mechanical behaviors, for which the relation becomes nonlinear, and we have to compute linearization of the stiffness matrix that is used in the computation. And I'm going to quickly say how. So the model we used is the von Mises-Hill plasticity model with mixed linear hardening, which is a base model for modeling plasticity. And it's particularly suitable, for instance, for metals, which are, let's say, materials deforming in a simple plastic way. And here you have stress-strain curves illustrating what I was saying before. So in one dimension. You can see here on the left that when you're dealing with elasticity, the relation between stress and strain inside the material is purely linear. And if you stop deforming your material, it will go back following the same slope to its original shape with no remaining strain. Whereas on the right, when you're dealing with plasticity, you can see that at some point during the deformation, if you pass a certain stress threshold, which is called the yield limit, the material starts to yield, and basically deformation occurs much more easily inside the material. And so the relation between stress and strain becomes nonlinear. And you can see that also if we release the deformation imposed to the material, it will go back to a rest shape, which is not the same as it had initially, because now you have some remaining plastic strain due to the plastic deformation. So very briefly, usually when using elasticity, the relation between stress and strain is explicitly expressed in the computation, thanks to the generalized Hooke's law. But in plasticity, this relation becomes nonlinear. Actually, we don't use an explicit representation of the relation, but rather we switch to an incremental solution of the equations, allowing at each time step to compute a linearization of the behavior law, so plastic linearization of the behavior law. And this allows us to compute an increment of stress from the current increment of strain. And this increment of stress is computed so in a plastic way, thanks to what is called the radial return algorithm, and it allows to compute plastic internal forces. And yeah, the last thing I'm going to mention here about the computation itself is that, as I said before, we are using 3 degrees of freedom of strain to represent the Cosserat beam model. So this means that in all plastic computation, we use 3-dimensional tensors, like in reduced tensors, which allows to reduce a lot the computation and save computational times, obviously. So I was a bit quick on this, but I'm mostly to show you applications of this model. Historically, the discrete Cosserat model was used at Defrost, for instance, to model inextensible cable in soft robotics. But it's also useful to model structures such as catheter or guide wires in medical applications. So now I'm going to talk about two applications that we are currently working on in the team. So the first one is the implant of a cochlear device, so which is something that is used to treat certain kind of deafness. And you can see here on this picture that the implant has actually two parts, an external part, which is fixed on the head, and an internal part with wire-like structures that is introduced inside the cochlea, which is a bone structure. And so if I show you on an animation what happens. So I hope you can see the video. You can see here that the wire-like structure is actually introduced inside the cochlea by pushing on it. And when doing so this is an electrode basically, and it's metallic. And when doing so, you have plastic deformation occurring on this. So if you want to be able to model correctly what happens during the interaction between the electrode and the cochlea, you have to take into account plastic deformation. And this is necessary, for instance, if you want to robotize such type of intervention. So yeah, and the second example I'm going to illustrate the usefulness of plasticity with is related to the SimCAD project, which I'm part of, which is a European project involving, as you can see, a lot of teams. And the general objective of this project is to demonstrate the usefulness of simulation in order to replace or partially replace clinical trials or preclinical trial phases when a device or a treatment is about to be released on the market. So here it is focused on heart diseases, obviously, as it is called SimCardio test. And the particular instruments we're working on is pacemaker lead. So if you're not familiar with what a pacemaker looks like, you can see here on the picture that it's actually composed of a generator and a lead, which is once again an electrode surrounded by soft materials. And this lead is navigated inside the vessel and fixed inside the heart to deliver then an electric signal. What's important here is that the lead is actually something that is pretty soft. So it's good because it's less likely to damage structures inside the heart. But the drawback of this is that it's hard to navigate it because of the softness. And in order to place the lead inside the heart, the physicians use what they call a stylet, which I hope we can see here on this video. It's the thin metallic wire that we can see here between the hand of the physician, and you can see that. Sorry.
We do see the wire.
Okay, cool.
I mean, I do in the video.
Cool. So you can see that this metallic wire, before inserting it in the lead to facilitate the navigation, it's usually pre-bent by the physician in order to facilitate the placement inside the heart. But obviously what happens here is that the stylet undergoes a huge plastic deformation. And so it's useful if you want to model navigation in a proper way to be able to model the plasticity phenomena occurring in the stylet, because they will have an impact on what happens during the lead insertion. So with this type of models, we're able to estimate, for instance, contact forces between the stylet lead and the vessel walls, stresses inside the lead, and then estimate the fatigue inside the lead to anticipate when it's about to fail. And yeah, to finish, I'm just going to show you an example video of the type of simulation you give. So here it's with a very basic anatomy, which is not realistic at all, but you can see that this stylet here is modeled with a Cosserat beam model. And thanks to the simulation, we're able to navigate it in the anatomy and to compute on the way the deformation applied on the anatomy thanks to the stylet. And you can see here that once the session is stopped, we're also able to compute the deformation of the stylet due to the, in this case, the heart beating like motion. So yeah, that's pretty it. And the last thing I wanted to say is that the ongoing work regarding this is the implementation of coaxial beams in order to be able to simulate more accurately combinations such as stylet and lead or catheter and guide wire, and also validate this type of plasticity models on versus experimental data. So thanks for listening, and if you have any questions, I can answer them now or later in the breakout session, just after, actually.
Thanks a lot, Camille, for the very nice presentation and the very nice videos as well. I mean, the applications that you are showing. There is a question directly from Stefan. I'm going to take it. How do you measure the plastic threshold, the yield of, for instance, the cochlear implant? And also for plastic material, the initial rest shape is not always well defined. How do you measure that? So the first question about the plastic threshold, maybe? Yeah,
about the plastic threshold, basically you have two options. Either you have very simple materials, not like the structures I was showing here, and then you can find the plastic threshold is something that is documented in literature, for instance, for classic metallic alloys or things like this. But obviously, when you're considering complex structures such as electrodes or leads, which internally are way more complex than just a metallic wire, the idea here is to use a homogenized model and to tune this model thanks to experimental measures, for instance, in uniaxial tensile test or bending tests. And yeah.
And the second question was for a plastic material, is the initial and rest shape is not always well defined, and how do you measure that?
Yeah, actually, this is a tricky question because basically, naturally, you will always have plastic deformation. I mean, things are not deforming purely elastically, and it's hard to say at like if you have something which is for which you have an initial deformation, then it's easy to say that, okay, before we didn't have any plasticity history. But if you're using something that, for instance, has been manufactured, has been stored in sealed packaging or something like this, you could always have some kind of pre-deformed shape before using it in the way you want to use it. And then it's hard to say that what type of plastic deformation you want to simulate to reproduce that, because if you don't have really the history of deformation that your material underwent, it's hard to say which type of deformation you should reproduce in the simulation before simulating the real application you're interested in. I don't know if I'm clear in this.
So I think it was, and anyway, I think you'll have the time here for, yeah, Stefan said yes, and thanks, Camille. Let's, I suggest for Benjamin, there was a question about Cosserat and another question about from Eligius about Cosserat as well. To move in breakout rooms, I think, so I can maybe just shortly share again the slides here. And there we are. So just as before, so each of the 4 presenters will be in specific subrooms, so 4 rooms. Room number 1 will be for Stefan about the prostate phantom. Room number 2 for Martina about the intraluminal procedures and robotic assisted intraluminal procedure. Eleonora for the framework on autonomous surgery. And finally, Camille about plastic Cosserat beams. So I think we're gonna move into breakout rooms. Guillaume, are you ready as well?
Yep, I'm ready.
Perfect. So again, speakers will be moved directly into the appropriate room, and guys, do not hesitate to join them for asking questions. There will be a poll as well. Again, that should appear sometime in the breakout.
Yep.
So the breakout rooms are created now. The speakers have been moved. You can just go and select the room you wanna go and ask questions. So I see already Adi has joined Martina in room 2, Vanessa as well. So go ahead, ask questions to the speakers, and yeah, that's very good. Thanks, Guillaume, for taking the presenter. Right. And welcome back to the main room. Okay, we are so back in the main room. I'm gonna again share, just for the transition, share the slides here. Okay, maybe you'll need Guillaume to stop the poll. If you did not do this so far, do not hesitate to vote for. There have been some poll if you want to give some answers. And Guillaume, maybe I'll let you close the poll in a few seconds.
Once I close it, there is no more answer possible.
So go ahead, guys, for the last replies on the poll, and then we're gonna move to the next session.
Okay, I close it now.
Cool. Thanks a lot, Guillaume. All right. Well, we're back for the fourth and before last session of today. That is medical simulation, and we'll talk about haptics, AR, and VR. We're going to have, again, 4 presentations, and for the last, we're going to have 3 presentations. We're going to start with a presentation from Infinitec 3D, the development company around SOFA, so led by Erik Pernod. Erik will present us Infinitec 3D, and especially the latest news about haptics and cutting. Serena from Genova will present us her work and the work at Genova University on a haptic simulator for surgical training. You'll see something on haptics, but a new kind and cheap way of making haptic devices, or at least input device, rather, I should say, from Jorg from University of Florida. And finally, we're going to have the presentation of Lorenzo from Politecnico Milano on microsurgery simulator. That will be the 4th and last presentation of today. So we'll start with you, Erik, if you are available and ready. So yeah, perfect. And he's already in his Infinitec 3D office, virtual office. Perfect. Thanks a lot, Erik, for making this presentation. Well, I think we're pretty.
Can you hear me well?
Yeah, perfectly well.
And can you see my slides?
Perfectly, yeah.
Okay. So thank you, Hugo, for the introduction. So my name is Erik Pernod, and first I would like to apologize in advance because I will have to cover several topics quickly, and I won't have time to go into a lot of details. And so today I will speak about recent results on haptics and cutting. So for people, just a few words for people who don't know me. So I've created Infinitec 3D, which is a company a few years ago now, to be able to continue working with SOFA because I love it. And as you know now that SOFA is open source, there's also its modularity allows it to have some open source plugin and also some private plugins. And so the idea of Infinitec 3D was first to integrate the main framework of SOFA inside Unity, and to be able to touch a bigger community and also to create some nice rendering. And then the idea is also to provide some consulting services around SOFA to be able to do some custom development and also to integrate your open source or private plugin inside Unity. And this allows us to continue working and contributing on the open source framework. So first, quick word about the integration of SOFA inside Unity. Just to say that I recently released a new version which supports the latest version of SOFA, so the 2012 and 2106. And it's also fully compatible now with the high definition rendering pipeline of Unity. So I will go very quickly on the integration inside Unity, just to say that in Unity, you can create what we call a SOFA context, which will create an instance of SOFA that will run in background. And the idea is when you create this context, you are able to access the main parameter of SOFA, so changing, for example, the gravity and the time stepping. Then you are able to load the SOFA scene either in XML or in Python. Load different plugins also, And the idea is that it's not a read-only mode. You really have access to the simulation scene as you would have access inside one sofa. And you can interact with the different components and also change the data and interact also with the Unity physical world. In terms of features, so we're able to recreate the normal, physical-based simulation, also to interact with different kind of haptics. So here with dual haptics. Then there's also it's also possible to use GPU computing. You can create also some particle fluid simulation. It's also possible to create some electrophysiology simulation, some molar drilling for dental application. It's also possible to simulate ultrasound and X-ray simulation, rendering, I mean. And so if you want to see more details about these features, I welcome you to look at the movie of last year's Symposium, where everything is detailed. And now I will speak more about the first recent work, which is the integration of haptic device created by Follow, so named Haptic Avatar. So in a few words, what is a haptic device from Follow? So it's composed from several devices, so with high performance haptics. So where you have some degree of freedom and also some force feedback on every degree of freedom and also on the grasper. It's a modular system where you can change the type of device. So it automatically detects the type of device you are using. This allows to create some very versatile and realistic simulation. And you can create some multidisciplinary setup, because you can see that you can create some a single user base, also some team training base, and developer base. And if you want to see more details, you should go to the Follow Haptics website. And Frederick Olson is also here in the event, and will be here in the breaking room if you have some question about the hardware. Now, how it works in so far. So basically, here is a type of articulation that you can do. This is represented in so far using the articulated system mapping mechanism, where you have first two rotation on the base and a different rotation. Then where you insert the tool, you have a rotation and a translation also. And depending on the type of tool, so for example, for a scope, you will have only 4 articulation, but if you are using grasping, there is 2 more articulation. Here it's how it looks, how the motion looks in so far. So moving in all the direction. So I wanted to record also myself moving the device, but I didn't have time to do it. And as I just described before, there is the idea of Follow haptics is that you can combine different type of device at the same time. So how do we do that in SOFA? The idea is that we have created so wall plugin to handle the device, where its own haptic device thread is created, running at 1 kHz. For each type of tools, we have a different component in SOFA that will handle the different articulation and also the possible interaction. Those devices are connected to what we call a portal manager, where you can set up the disposition of the different tools. And so each portal will define its own position and orientation. And if you are using some grasper, for example, there's also what is called an iBox controller, so which is in charge of handling the force feedback inside the grasper. This is a quick movie of 2 devices playing with the tools. So I did it quickly, so I did not have time to train a lot before doing the movie. And you can, so for the moment, there is no collision between the 2 devices. It's only interacting with the tools, with the deformable tools. And now I will move on to another topic, which is mesh refinement plugin, also known as cutting. So the idea is that we are going to subdivide tetrahedra according to the intersection of their edges. And so according to the paper data-driven tetrahedral mesh subdivision, there is 11 possible configurations. So those configurations have been created inside so far, implemented, I mean. And then we define the configuration depending on the type of input. So for example, a cutting plan. And the idea is to be able to support the mechanical, under the mechanical behavior. So first, you have the tetrahedra to subdivide. Then you define the type of configuration it belongs to. Then you need to also update the neighborhood to be sure that the mesh stay fine. And then you create the new tetrahedral mesh, and then you need to update all the components. So for example, in this movie, what is important to check is that I'm going to subdivide the whole mesh, all the tetrahedra, and the idea is that the mass of the cube is not changing. And you can still interact with the film. And in terms of application, for example, the local remeshing. So here, for example, are 2 movies of a sphere carving a deformable cube. On the left, there is no tetrahedral remeshing, and on the right, there is. And so you can see the difference of the size of the hole. And the second application is cutting. So first, using a cutting plan. So we cut the whole cube in the planned direction. And there is also some, it's also possible to cut from most inputs. Here, I'm using the mouse to select different tetrahedra at the surface of the beam. I'm going to first do a small incision, then I'm increasing the depth of the incision to continue to cut the beam. Whoops. Something wrong. Sorry. And just so last results is just to say that now we are also able to recreate the surface of the cut. So here, for example, I'm cutting a lever and I'm applying some new texture on the surface. Okay. You can still interact with the model and also on the surface of the cut. And last results, I wanted to record a movie that integrates both results of the follow haptic avatar devices and also the cutting, but I hadn't time to finish. So this is just a teaser where you can see the 2 grasper interacting with a lever inside Unity. So the next step will be to start cutting the fatty tissue on the lever. So thank you for your attention. And just to recap, both plugins are going to be released soon, normally in next month. The haptic avatar plugin will be open source, whereas the mesh refinement plugin will be private. So they are both nearly completed. There's still some little work to do.
Thanks a lot, Erik, for the nice presentation. Yeah, there is a lot of reaction in the chat. There is a question from Sergei asking, so first, thanks for the presentation. My question is why the Unity engine has been selected, because it's C# as a base for the development and not Unreal, for instance, it's C++ or Godot, which is open source.
Very good question. So at the beginning, I wanted to do both engines. In fact, we already have a concept of SOFA inside the Unreal. And the answer is just that I had several contracts to work with, to do some development inside Unity. And so this is the only reason.
And I'll add one. So yeah, there is a question for Andrea if the video are actually accelerated regarding the cutting simulations.
No, not at all.
And yeah.
In the breaking room, I could maybe give some numbers because I don't have it right now, but it's a few milliseconds to do the cut. To perform one cut. What starts to be long is to start doing some topological change at each simulation step.
And if you want to see more furry simulation, fairy tales, and so on, just join Erik in the breakout rooms. Guillaume is saying, "Oh, that's definitely the king." So that's yeah. Thanks a lot for the presentation. Maybe just one last word. It would be how people can actually connect to you and collaborate with you. Is there any condition, or yeah, how could we actually work with you?
No, just to contact me and discuss. I will be happy to discuss.
Okay, cool. Thanks a lot. We'll move. So there will be time to discuss with Erik at the breakout rooms at the end of the 4 different presentations. Next presentation will be Serena, and then it will be presentation of Jorg. I see Jorg is already in the starting block. Welcome, Serena. So that's going to be a presentation on again haptics, but this time there will be multi-sensory feedback for the users. So presentation from University Genova. It's a pleasure to welcome you for actually the first time at the SOFA Week.
Right.
The floor will be yours. I think you'll be able to share your screen anytime. Yeah, perfect.
Okay. All right. Okay. You should be able to see my screen.
Correct. Yeah, we see the. So we are already at the result. Yeah,
right.
no spoil. Okay, perfect. Thanks a lot,
okay.
And welcome on stage.
Thank you very much. So my name is Serena Ricci. I'm a postdoctoral fellow at the Center for Event Simulation and Learning at the University of Genova in Italy. And today I will be presenting our project about a visuo-haptic simulator for surgical training. So this work is the result of a multidisciplinary collaboration between the Department of Informatics, Bioengineering, Robotics Engineering, and System Engineering, together with the Center for Event Simulation and Learning. So basically, our project started because our goal was to improve the medical knowledge and medical training, specifically in the surgical part. And we all know that right now medical students have to learn multiple manual skills, and which whole involve haptic feedback, haptic sensing. And I'm thinking about incision, I'm thinking about suturing, but also like palpation of like biological tissues to recognize pathological signs. And right now, so here in Genova, we are very lucky. We have a very amazing simulation center, which uses either mannequins or artificial body parts, as the one that you can see here in the picture. However, artificial body parts have the downside of being we need to frequently replace them, because the first student that starts using the skin patch, which is the one that you see here for performing incision or suturing, would have a different feedback with respect to the very last one. So basically our idea was to try to substitute, or at least partially, like these artificial body parts with something which could be used like multiple times with no differences, high repeatability. And so we like opted for, like, we decided to investigate the world of visuo-haptic simulation, because visuo-haptic simulation has the advantage of providing both like haptic and visual feedback at the same time. And also a software-based simulator has, of course, the advantage of providing also performance feedback and real-time like cues and feedback. So basically, our idea was like starting to create like a simulator which could be used by medical students, something which could also be low cost and like relatively simple to use. We started from the Geomagic Touch. I'm sure you all know this guy here. So we had a low-cost haptic device, and we started adjusting the end effector of the Geomagic Touch to make it look like a surgical like handle. So basically, we 3D modeled and print two handles. The first one here is like the terminal part of a scalpel, while the second one is a needle holder for like actually letting students using the device in a correct way, as they would use the real surgical tool. The reason why I'm here today is because we decided to start for the first time in our lab. So I look forward to receiving suggestions and comments using SOFA. So basically, the first thing we did was to model a skin patch. We decided to model a single layer skin patch because we didn't have, like we wanted basically to start like exploring the skin a little bit. So I just put it some like parameters here. I'm not gonna go into details as time like runs super fast. But after the skin patch, we also modeled and like started playing with the surgical instruments, and we decided to use 3 different surgical instruments, a scalpel, a capsule, and I will show you how did we use it, and also a needle for suturing. We studied different collision points, as you can see here, 3 for the incision and 2 for the suturing at the 2 edges of the needle, basically. I mean, this is like a super probably standard and super basic information for you guys, but the idea is that basically we wanted the medical students to interact in a realistic way with the actual like 3D model through the haptic device and vice versa. So basically, we have implemented 3 tasks, an incision task, a suture task, and a dexterity task. So the first 2 have the surgical counterpart, while the second one, like the third one, sorry, on the right here, is a dexterity task, which is largely used by surgical residents to basically to learn how to perceive depth, especially in minimally invasive surgical training. Again, I'll go super fast and then we can discuss together at the end. So this is how the incision looks like. So basically, we decided to like put 2 skin patch close by, and basically the user could actually cut through the like middle line. For the second task, we implemented the suturing, and in this case, basically the user has to pass through. We put some spheres. So that students could learn where to pierce the skin, and also the spheres change color whenever the students pass through them in a correct way, and this is how the suturing looks like. And the third task is the dexterity task. So in this case, the user has to pass through the rings without touching them, basically, and also there is a skin patch at the bottom so that students can also take advantage of the haptic feedback while performing the task. In this way, they can realize how deep the capsule is passing through, basically. And again, we have like changing colors whenever the ring is actually touched. So after having implemented these 3 tasks, we tested our system, and we basically tested our system on 16 participants, 8 experienced surgeons, with an average experience of more than 20 years. And we also tested the same simulator with eight age-matched control subjects because we wanted to assess whether, so basically we wanted to do two separate things. On one hand, collecting feedback, and on the other hand, also collecting performance metrics to see whether this type of simulation was beneficial, at least equal to the basically the traditional training. And this is like, for example, one subject, a control subject, I guess, like by watching how the person is moving the hand effector passing through the rings in the dexterity task. I'm gonna go super fast to the main results we found, especially for what concerns. So basically, we asked participants to fill out different questionnaires. We created one questionnaire for collecting feedback on all the aspects of the simulator. So hardware parts, the physical part, feedback like haptic feedback and visual feedback. For the incision task, I'm sure you could have like experienced yourself what was kind of not evaluated in a completely good way was like the cut, because in order to make the simulation fast enough for the students to perceive it as it was a real cut, we basically put some we check collision points in a sort of very rough way, so the the cutting didn't really look super realistic. However, the resistance and the force feedback provided were both perceived and enjoyed. We can say enjoyed by the participants. For the suturing, participants like, of course, the 3D printed needle holder because the movement of suturing is a very specific one, and also the feedback in camera position. Participant, especially experienced surgeon, didn't really rely on the force feedback, and what was kind of we still need to work to is the skin dragging, which is not super realistic so far. I mean, it is realistic, but it's somehow too hard, especially the stiffness perceived. Finally, for the dexterity, again, participant color changing and capsule, the possibility to see, to have a feedback. We need to keep working on the camera positioning and the depth, and also participants were kind of stressed about the depth perception, but this is a typical feature of the task. So it's probably not related to our task, like the virtual task, but the task itself is a very complicated one. Of course, we are still working. This is a very first prototype. We need, and we look forward to see whether there are people interested in collaborating with us or giving us feedback or suggestion. We need to work on the, of course, haptic feedback, so tuning parameters even more, visual representation, so color, texturing, and many others. We keep working on providing visual cues and suggestion during the task, as well as after the task, because we found feedback a very good starting point for clinicians. And of course, we need to validate our system, improve it, and also we want to move it to bidimensional tasks so that participant can actually perform the surgical tasks as they would do in the real world. I'm gonna finish. I think I was kind of okay with the time, so I put it here, our repository on GitHub. If you wanna download our team, our project and try it and give us feedback, and of course my email in case you need, you have more curiosities or questions, but we can meet later.
Thanks a lot for the presentation in time and so on. That's perfect. Yeah, that's great, and that's also great to see new faces and new projects ongoing around the SOFA platform. Is there already some questions in the audience? I don't know if so. Yeah, if there was the mic activated, maybe it was for a question. Do not hesitate to unmute yourself. If there is any other question, guys, do not hesitate. So for Serena, it's going to be obviously room 2 for the breakout session. What I can already tell you as an input is, as you might have seen from just the previous presentation from Erik, is that for cutting, you have a dedicated partner, I think, which seems pretty straightforward there. You would have another partner, and maybe I'm thinking more about suturing, where the company, which is called Insimo, is working a lot on that kind of topic. suture. So that's all depends the level of complexity you want, because going really far and really advanced as a haptic feedback, modeling of the, for instance, the wire, I mean the suturing wire, that kind of things is on a simulation standpoint quite complicated. So they worked quite extensively on that. And another remark was regarding the evaluation. You did that in your own simulation center at University of Geneva, is that correct?
Yeah, exactly. So yeah, this is another point. Like, so if, like, I know maybe sometimes like finding clinicians or medical students can be like hard, like tough. So yeah, so we have a pretty extensive.
Yeah, that's cool.
Group.
That's
yeah.
And I think on the in the other way around, I think it could be interesting for other partners to collaborate with you. So for these reasons. So, and yeah, could you? It was a question I was almost forgetting. It was the question posted by Arno. Would that be possible to post also the link of the GitHub in the chat so that people can take a look at it and
yeah, sure.
start it on GitHub and download it and so on and so forth.
Yeah, I will agree. Right now. Yeah.
And it's, I think, and it's the same question for Erik. There is people eager to. Oh yeah.
Oh wow! Thank you.
People are already doing it. So François Jorg is actually one of. He's actually the research lead at INSIMO. I was mentioning the work on suturing, so he would be also a very good contact point for that for the topic of suturing.
Okay, thank you.
I think you're going to have some downloads of your GitHub repo from what we can see. Is there any other question from the audience, guys? So I'll let the mic open a bit. I'm going to check out here. Okay. Did I hear another mic than mine? No, not for the moment. And definitely we could also discuss further, also in the breakout room, you know, the model itself, how you actually, as you said, how you tuned it in SOFA, and what you would actually need to improve here. But that's I mean, what you're looking for as an improvement. But,
yeah.
If there is no other question, Erik, François, and so on in the chat, I suggest if there is, we can take one more if you'd like. Otherwise, we're going to switch. We're just 5 minutes. We have just 5 minutes of delay, but yeah, we're gonna move. We can move on, and again, keep your question for Serena for the break at 3:50. It will maybe be 3:55. But thanks a lot again, Serena, for applying for a presentation, making the presentation, getting connected to us, and I think you'll get people that will get back to you pretty soon.
Thank you.
We're going to move from Italy to the US now with Jorg from University of Florida that we have the pleasure to welcome today, that will present us a new kind, and you'll see very advanced in the way it has been actually thought. But I'm half serious, I'm joking, but you'll see it's really an interesting way of approaching things. A 4-DOF input device for interactive simulation in SOFA that you can actually do on your own. So, Jorg, you should be able to share your screen freely. And
merci pour l'introduction. Écran, application. I'm doing it for the first time here. So, écran, is that what we are partaging?
Screen. Yeah, partager, sharing screen. So, sorry, it appears to be in French by default.
No, that's fine, but it's the application or the écran?
Application is just one app, like a browser or whatever, and écran is the full screen. I mean, sharing the whole screen.
What do you see now? Do you see me?
For the moment, we see you. Yeah, only you. There is no screen sharing or.
There's no screen sharing. No. Okay, so there's only a cancel. That's very strange. Entire screen cancel. Sorry, partager le contenu. Share, and I click. The share is not clickable, only cancelable.
Maybe is there the sufficient rights? Maybe for does your browser? Yeah.
Does my browser? My browser usually. I mean, I'm only using Zoom, but.
Okay, I think you have to click on the screen before.
Optimization.
Sorry, Camille is right. You need to select the screen. It's actually not clickable, but you need to select which screen or which application you want, and then it's going to become clickable.
pour le mouvement. It's not optimized.
Thanks a lot. Thanks a lot, Camille, for the update. Because you're, yeah, I think you're correct. So if you start again making partager, sharing, yeah, perfect.
Do you now see something?
We see something happening. I'll tell you what we see. Yeah, we see your presentation. If you go full screen, I mean, if you go for, yeah, perfect.
Love it. Okay. Sorry about the delay.
Perfect.
All right.
No problem.
So first of all, I'm so thankful to the SOFA community for all the software, and I've been a great fan, and we're using it for surgical simulation, same as the previous two speakers who gave fantastic talks here. So I'll give a very short one here. A 4-degree of input device that you already own. This is a cell phone, and this is a, well, you may not own this one here. You may not own a cell phone pen. This is SOFA running remotely with simulation of surgery, laparoscopic surgery, and this will be the laparoscopic surgery input tool. Now, if Follow You had been there and it hadn't been COVID, I probably would not have thought of all of this. I don't have to give you the background because it was already explained what laparoscopic surgery is, but the main thing is you see everything on a flat screen anyhow, just as if you go back here, we see it on a flat screen, and we have these tools that are sticking into the body, and very often we use this kind of devices to model that. We see one down here from now almost 10 years ago, where you are modeling what is actually incorrect. This has 6 degrees of freedom around, up and down, and so forth. And you can also tilt the, let me go one back. You can also tilt the pen here, and similarly here you can tilt that. All of that is 6 degrees of freedom. It's actually more than what you want. What you want is just 4 degrees of freedom, because the patient wouldn't like if you were to move in the X or Y direction on the body. So you have 3 degrees of rotation and 1 degree of pushing the tool in and out. That's the 4 degrees of freedom that I was mentioning. And if you just looked at the Fallu device, well, that would have been wonderful to have at that point. But this idea came to me at the beginning of COVID. And anyhow, we had been developing all sorts of gadgets. For example, this one here, where you see 3D printed with PVC pipes and then wiring running inside the pipe. But typically people don't have that conveniently at hand. So they have to go to places to find such a tool. And then, of course, if it's handmade like this, it will at some point break. You won't know about it. And all of that, needs a large overhead. Now, of course, if we had access to this, I just looked at the pricing. Maybe someone can tell me afterwards about the pricing of this good Follow You tool, which seems just perfect and really robust. Anyhow, we didn't have that. And so what we did instead is we used a cell phone. In fact, I used my Android phone to start the whole thing off. We used the motion sensor for tool orientation, the touch screen for in and out motion. That gives us the 3 rotational and the one extra degree of freedom that we need for moving the tool in and out. And then the volume buttons we chose as tool actions. So if we want to cauterize over here, we press that button, and we give modulated vibration for the haptic feedback. Then, of course, there's some coordinate systems we have to deal with, but this is basically it. So there's nothing like having a look at it in practice. So the simulation is actually running in a different place. So that's why you see Rainway. We used to use Rainway as our remote display. Now we have our separate one because we didn't think that Rainway was safe enough. And you see the surgical tool here being prepared. So some kind of pairing going on and registration with respect to it. And now you hit the trocar point. So nothing moves unless you touch the pen. And the pen can be put up in many different ways. I'll skip a little bit ahead of time so that we catch up with some of the time that I wasted by not knowing how to get that application to show.
No problem, Jorg. You're in time. No problem.
Okay. So basically, you see on the screen everything moves together with this here, and now we ergonomically improved it by putting some graphics card boxes underneath. That makes it work much better because it has the right angle for your arm. And so usually people don't have two cell phones, and so we use the mouse as the weak hand. And that typically takes the other clamp that can retract fatty tissue so that you can expose it and then tear it or cauterize it. Now we can change tools. That in the meantime, we've changed the changing of the tool because it's a little awkward to reach down to the keyboard. But all the action that you see here is done by the cell phone. So the snipping of the cutting tool is by pressing the button. So it's a hardly perceivable the motion here with the hand. And the hope is that cell phones are sufficiently ergonomic. The size of a typical cell phone is roughly the size of the amount of space you have in the abdominal cavity. So that works out rather nicely, so you don't have to enlarge it or make it smaller, but you could scale it. All right. Now, and so this is the layout. The one that you just saw a moment ago, we still went with different setup, but the current setup for what we call TIPS Lite. TIPS is our simulation environment toolkit for illustration of procedures in surgery. And this is TIPS Lite. And so we have a sofa, of course, as the core on a remote server that then talks to our thin client. So you can just have a laptop somewhere sitting at home, and you can pull out your cell phone, and with that you can practice laparoscopic surgery. You may think this is a little ridiculous because how is the feedback good enough? How can you really learn something from it? Our goal is not to do what just a moment ago in the previous talk, the goal was to actually fine-tune your motion. It's to experience a sequence of procedural steps. And so the precise motion is not, or the precise motion is very important, but it doesn't have to be realistic what we're doing to the point of thinking that it's a real tool. You're having a cell phone in your hand. And so it works very well with our overall goal to basically actively illustrate. And so that's it. Questions?
Thanks a lot, Jorg. There is actually a lot of reactions in the chat. First, yeah.
If I find my way back, I'll answer it. So, yeah.
Yeah. So for the moment, there is no question in the chat. So please, anyone, feel free to unmute yourself and ask any question you'd like to Jorg. You have it created a lot of reactions and so on. So first, Frederick from Follow said that you were actually killing his business. There was a view saying that it was not simple GPU boxes, but medical GPU boxes that you are actually using. So yeah, that's and you said it looks ridiculous. Actually, I think no one actually think that here. I've been discussing this project with various academic and industrial partners that are actually quite interesting in always getting things simpler. That's why I wrote the KISS principle. which is more than just a French technique, and you can really. I mean, I think there is really way for using that on various topics. So, Erik, you have a question?
Yes, just wanted to ask a simple question. What are the next steps for your project, and what do you want to develop after?
So the project that I presented here, you need to have apps both on Android and iPhone, and it needs to connect from the iPhone to the PC. All of these pieces now work. The one thing that's still left is to connect the iPhone to a Mac. So it's quite interesting. Bluetooth, we're now using Bluetooth. Bluetooth should work. It sounds like a standard. Turns out not to be. Turns out that Bluetooth from an iPhone doesn't talk to anything else, and the walled garden, and all of our collaborators in the medical crowd have iPhones. So the fact that we can do wonders with Android doesn't really help them. The other thing I wanted to quickly answer, there's no way that I'll be one of the first buyers of Follow You, if it is affordable, of course. But there's, of course, a disadvantage in that you only have a cell phone. You only have vibration when you hit something. It's not the perfect ergonomics. A cell phone doesn't feel like the scissors that you might, end that you might have interacting. But to me, it has been very liberating because we were always on the software end, and admittedly, all of our hardware stuff was sort of an afterthought. And the complexity of having to deal with different versions or non-evolving versions of the Omni has always annoyed me.
Thanks a lot for the reply. You have another question here from Frederick saying, so the insertion is controlled by the mouse?
No, the insertion, so there are two tools. The weak hand just uses the mouse in a almost 2D fashion to grab fatty tissue and pull it. The right hand does everything, in, out, and or in my case, the right hand, sorry, I'm right-handed. The strong hand does everything with the cell phone. The exact motion in and out, that's why we have this cell phone pen sticking up. So it's like a finger. If you had three hands, you could use your third hand to have a finger and run your cell phone over your finger. The in-out motion is exactly what you have on the screen. So it's super precise because you know how to type on a screen, right? So it's a millimeter precision, what you get. So
you just got with all your innovation a discount from Frederick. So on Follow Haptics. So do not hesitate to get in touch with them. I think that's what I wrote actually more seriously above. That I think it could be it could lead really to interesting I think thoughts and results so that you to connect. Maybe you already did last year at the SOFA week, but yeah, I think it would be very interesting, and there is other partners that would be interesting definitely. So thanks a lot, Jorg, for sharing this very smart and simple idea, but therefore powerful idea.
And thank you for all the wonderful software that I get to use.
You're welcome.
Really,
Pierre is asking a question. Pierre, is that fine for you if we keep it for? And same for Erik, if we keep some questions for the breakout room, so you'll be in room number 3 for you, Jorg, and we'll move to the very last. If it's fine, is that fine for you, Jorg, as well? Will you be available?
Can you explain to me how to get to the breakout room later on? Not now.
Yeah. No worries. We'll take care of you right after. Okay. Thanks again, Jorg, and it will be the 4th and last presentation of this medical simulation haptics AR and VR session. Right now, Lorenzo, you'll be able to come on stage and especially sharing your screen. Yeah, welcome, Lorenzo.
Hello.
So I had the pleasure to meet Lorenzo just a few days ago, and we had already some emails together before, but working on SOFA quite recently. It's a pleasure to have you on stage, and he will present us his work on microsurgery simulation.
Yeah, we're on the non-haptic side, let's say. So we are on a completely different level. So let me share the screen.
Yep. It seems to be starting.
Okay,
and
you should see it.
Now we see it. Perfect. Yeah.
Great.
The floor is yours.
First of all, thank you. Thank you for the SOFA team, for the entire team for organizing this event, for the occasion of presenting our work. I'm Lorenzo Civilla. I will present my master thesis at Politecnico di Milano, supervised by Maria Chiara Palumbo, and with the collaboration of the Medical University of Vienna. The title of the work is Microsurgery Simulator of a Cerebral Aneurysm Clipping with Interactive Deformation in a Mixed Reality Environment. So the context, unruptured intracranial aneurysms are bulging situations of an artery that occur inside the brain due to a variety of risk factors. Their preventive management can be performed by means of two main modalities, surgical microclipping or endovascular coiling with or without additional devices. In recent years, the endoluminal approach is adopted more and more, causing a reduction in surgical expertise when performing the clipping procedure. That being said, the surgical approach, that is the microclipping, is often the only possible solution. So it is crucial to the surgeon to handle this kind of surgery in the best way for a successful procedure, relying first of all on his own experience. In this work, we aimed at developing a solution that will have an impact in supporting the surgical training, preparative planning, and maybe intraoperative support as well. The aim of the study has been to develop an application able to let the user grasp better understanding of the entire cerebral anatomy and thus the specific aneurysm to be treated, thus different clips and different approaches. From this, the specifications derived are, first of all, to reproduce patient-specific models with a high anatomical realism. Moreover, to have a good physical realism, we also need to simulate tissue biomechanics and clips mechanics. And obviously, we would like to have a low cost and a highly effective solution. The best solution, the best structure that we identified is an application, a real-time thumb simulation of aneurysm and clip with holographic visualization and manipulation to merge the advantages of a high computational power PC and the 3D visualization of a mixed reality head-mounted display. In our case, Microsoft HoloLens. First of all, the scene in SOFA has been written using the SOFA Python 3 plugin. We used Euler implicit and conjugate gradient solvers and ray tracing for collision detection. The implementation of the aneurysm model has been done with triangle fan force field for the linear elastic behavior, surface pressure force field to implement an internal pressure of 90 millimeters of mercury, and rest-shaped springs to simulate the connection with arteries at the cross-section at the boundaries. The clips have been designed and implemented with joint spring force field. This allows a realistic closure of the clip as a rotational spring, and a constant force field that is opposed to joint spring to control the opening of the clip. The holder instead has been modeled as a rigid body, fixed, controllable in the position. So in the end, SOFA has been used just to simulate the interaction between the clip and the aneurysm. Then, in order to have an anatomical realism that we were seeing before, all the other visual models belonging to the head were included in the holographic scene. These models were created starting from the segmentation of the patient, of patient-specific images, and freely available 3D models to make the scene more realistic. And since the development of HoloLens applications are done in Unity, including the integration between SOFA and HoloLens, the models have been imported in a new scene in this software. In Unity, a scene is described in the form of a graph with shared models between SOFA and Unity itself. The shared visual models between SOFA and Unity have been imported in Unity to allow their holographic visualization and modification. And then UDP communication protocol has been developed between SOFA Python 3 and Unity or HoloLens, depending if we're working on PC or in the mixed reality device. Unity or HoloLens sends the positions of the holder at every run of the update method. And while SOFA sends the positions of the vertices of the simulated aneurysms and position and orientation of the clips at every run of the unanimate begin event method. Obviously, when the data are received, all the elements are updated respectively in SOFA or in Unity. Then, to simulate as much as possible the manual operation of the instruments during the surgery, we took advantage of the HoloLens interaction methods, trying to avoid the keyboard controls that are always possible using SOFA Python 3. The first solution, on one hand, we have the use of manual tracking in HoloLens 2 that is intuitive, quite precise, but you don't have any instrument in your hand. And in the other hand, we have the use of an image target with an additional tracking engine that in our case has been Vuforia. We used a half-cubic multi-target that is compatible with both HoloLens 1 and 2. The final UDP protocol allows to maintain the SOFA and Unity processes separated, allowing to have the maximum performances of both. And in fact, we obtain between 3 and 7 milliseconds of time step computation and an update frequency of 20 to 60 FPS. You can see in the left a sequence of shots that the manipulation in HoloLens 1 look pretty realistic and works smoothly. And the entire application, the final application, has been called HoClips. In HoloLens 2, here is a video. I hope you can see it. You see there is a menu, the holographic objects, and there is the scene in SOFA that is animated, started. In the augmented environment, we can interact with the holograms. We can manipulate the objects to replace them. We can select a clip from a menu and start the connection with the scene in SOFA, again interacting with a button. The objects can be manipulated with a manual tracking, as I said before. And again, with the hands, we can further manipulate the holograms, for example, making them larger or repositioning them or reorienting them. And we can also select the structures to visualize in order to better understand. In this case, we have hidden the head in order to show you better how the entire simulation works. You can see how the scene in SOFA is modified as the holder is moved, as the position and the orientation of the holder is changed. The holder is placed in position. The clip is opened with a keyboard control to reach the aperture desired, and once repositioned in a configuration in the desired configuration, the clip is slowly closed and the aneurysm is deformed accordingly. You can make obviously different attempts of positioning the clip and the holder, and to obtain the final desired configuration. And once the final solution has been achieved, you can activate back the anatomical visualization to see if the approach is actually feasible, evaluating intersections with other meshes. So this was the result, and for the future, we are planning to expand the set of clips and approaches simulated in HoClips and implement voice commands for the opening and the closure of the clips. We would like to simulate craniotomy as well, and integrating it with animations developed, for example, in Blender. We would like also to include other structures like brain or other active elements or tools. And it would be nice also to test the TCP protocol instead of UDP as well. And yeah, if you have any question, I'm here. I would like to answer them. And here is references, our contacts. Maybe, yeah.
Thanks a lot, Lorenzo, for the presentation. Right in time, even like 10 seconds in advance. So that's perfect. Thanks a lot for the presentation. It's actually, for me, it's almost, I think, one of the first time I'm actually seeing, especially in a video, in a 3D view so far with HoloLens and so on running. So it's not something I'm seeing quite often. So it's cool to see that happening. Is there some question for Lorenzo, and maybe there would be also, I think Maria Chiara might be in the area for other questions if it's
yes, I'm here.
More perfect, ciao Maria. So if there is any question for Lorenzo, please do not hesitate to unmute yourself or post something in the chat. Maybe there is people already writing things in the chat. I'll start. It will warm up people with a first. As I said, it's cool to see the HoloLens plus SOFA application, to see even that with a SOFA Python 3. I see Erik is already here. I just wanted to get a refresh of what you already told me, but is that using Lagrange-based constraints, so like a free motion and a constraint solver, or is that using penalty-based approach?
It is used penalty, and yeah, in the slide of the SOFA implementation, I displayed also the contact stiffness parameters, but I missed it. Okay. Go too much in detail in that because of time and to show everything. But yeah, it is penalty, and for now at least. But it would be nice also to try the Lagrangian to see how it works. Sure.
Yeah, when also seeing a previous work of this morning where there was a lot of things on making matrix assembly faster, so basically solving the system, advanced systems most efficiently and keeping the accuracy quite high, especially when we are using constraints. So it would be nice to couple those. I know some research team and also Insimo worked on the topic of aneurysm clipping. So as we said, I know I already said that several times, Mike, but if you wanna test it sometime and so on, let me know. We could make a way to get the right connection. Okay. I just need to freeze my own. I just take a bit of time and that's it. Erik, please go ahead.
Yeah, just a quick question. I never use the HoloLens, but I assume there is no haptic feedbacks on your hands.
No.
And is this a big issue? I mean, how do you contain your movement if you have no feedback?
No, actually, you don't have any haptic feedback, and that's true, as I was saying at the beginning. Actually, there is no containing in the, you have no movement constraint. You can have, as I said, the concentration between meshes. That is something that you do not want. But for example, you can implement some kind of visual alert when you have the concentration between meshes, or noise alert, because HoloLens also have the possibility to play some noises and are very direct to the user.
Thanks a lot for the question. And yeah, you see, so everyone is so that's what I feel guilty because it's actually what I was promising you, Maria Chiara. It's so both the remark of François and the comment of Christian are related to the code that could be actually could be shared. So it's something I don't know if you're I mean,
we took inspiration from the Christian Durier paper too.
Okay, but yeah, I think
we know it. Yeah.
Cool, and we could even, I think, push that further, like really comparing providing the code and comparing the methods. So it could be nice. Let's carry on the discussion. So keep all the questions you have for Maria Chiara and Lorenzo. That was the speaker. So thanks again, Lorenzo, for taking the time, preparing the presentation, coming here, registering to the event. It's cool to have again new faces with us. We're gonna have the breakout room created, and no worry, Jorg, we're gonna manage that. Where each of you, the speakers, Erik, Serena, Jorg, and Lorenzo, you'll be dispatched in the different breakout rooms, or the sessions, sub-sessions, as it is also called in French here. And yeah, you'll have further questions from the audience. We're going to take like a small 20 minutes, maybe slightly less, to try to recover the time. Guillaume, I'll let you the power and just splitting the rooms. Okay, thanks.
So I'm creating the rooms. Try to find by yourself how to move, but if you can't, feel free to put a message in the chat, and I will move you myself.
But for Jorg, in your case, Jorg, you'll move automatically. Okay, as a speaker, you'll undoubtedly arrive in the right room
in 2 seconds when I will click on the button.
See you in a second.
Okay, so everyone should be able to choose a room now.
And so I should be using rejoindre maintenant?
Yep.
Mm-hmm. It's funny to see people disappearing like that. Okay, I'll go myself into some of them. Maybe, yeah. Guillaume, maybe we should. I should not forget to update again about the voting for the award candidates. Maybe to remind that. I'm gonna keep a bit of text. Yep.
Okay.
Thanks. So we're back in the room. Sorry, we have been a bit. I mean, we had the countdown, but we have been a bit cut here. Erik, do not hesitate to write again your comment to Serena, because I just had the time to mention that. So do not hesitate to write as a private message in the chat. So a lot of questions again, a lot of things, a lot of things going on here. We're gonna then continue the session, and with actually the last, there was a poll. Guillaume, can you maybe close the poll? It will be the last seconds to contribute to the poll that Guillaume just sent. Thanks a lot, Guillaume. And I'm gonna share just my screen for a second before giving the floor. There you are. Okay, there you should be able to see my screen. Okay, so we had the breakout rooms. What I wanted to say is that do not hesitate again to vote for your favorite contribution on the SOFA Awards. That will be the last minutes maybe to vote here. And we're gonna start the last session for today about medical simulation, and rather here training and planning, but you'll see there will be a VR again with first Vladimir talking about a platform for hysteroscopy training. Second, tumor growth simulation, and it will be coupled to the open source viewing tool, which is one of the contribution of this year SOFA Awards, and an hybrid methods for realistic soft tissue deformation from Zara. So, sorry, I think the institution is not correct here. I should correct it, but yeah. So that's for the 3 sessions that's gonna start for now. Obviously, there will be after the 3 related breakout rooms. The first being Vladimir. Vlad, welcome to the SOFA Symposium 2021. I'm glad to have you again after meeting you for real back in 2019, I think, in Paris. I'd be curious to hear more about your updates around SOFA. So I'm gonna check. I could not hear you. Yeah, let's just make a sound test here. No, I cannot hear you. I don't know for others if you can hear Guillaume. I don't know if you can hear.
No,
Vlad.
I can't hear you.
I'm gonna stop sharing my screen. All right, and you should be able then to. Yeah, good. No, I cannot hear you. You should be able to on the right arrow close to the activation of the sound, be able to select the right. I'll let you know as soon as we can hear you. Okay, you'll reconnect, I guess. Yeah, that's where. All right, we'll see if everything is running fine for Vlad. Otherwise, Peter, I'm just gonna check if Peter is in the area. Yeah, Peter is here. So yeah, we'll check for Vladimir connection right after. So, and right after those 3 presentations, there will be again a time for discussion, and it will be the closing of today's session of the symposium with first the award ceremony, and second a short teasing for tomorrow's session. So for the technical committee of SOFA. Let's have a look. Vladimir, can you? I see you up here. Yeah, perfect. We see the video again. So we cannot hear you for the moment. Thanks a lot, Guillaume, for sharing the links. Yeah. Thanks, Christian. All right. Otherwise, if you want some time, Vladimir, so we'll let the last attempt for Vladimir to connect. Otherwise, Peter, are you available for? Yeah.
Should work. Can you hear me?
Yeah, we do hear you. Perfect. So we'll wait for just a second for Vladimir to reconnect. We'll see if the audio works. Otherwise, I'll pass on the left, and I'll give you the floor.
Could you let me know if it works now?
Yeah, perfect.
Perfect. Finally.
The magic operated.
Yeah.
Thanks a lot for making the effort of the connection. And yeah, the floor is yours. Present us your new VR platform for hysteroscopy training.
Okay. Enter screen. Okay. Does that work now?
Sharing just started. Yeah, we see ourselves. You can and go full. If you go full screen, it's perfectly.
Yeah. So good afternoon, everyone. I'm Vladimir Poliakov, and I work at K11, and together with Skulltech, we're developing a VR simulation for an office hysteroscopy. Now, since we had this tiny delay, I'll try to be brief and be more of an introduction to our use case. So first, let's start with a short medical introduction. Hysteroscopy is a type of minimally invasive surgery that is performed inside of the uterine cavity without any additional incisions. A clinician inserts a telescope, which is a slender telescope inside of the uterine cavity, to inspect it and to perform some surgical treatment if needed. Now, there are plenty of reasons to have a hysteroscopy, and up to a recent moment, the golden standard for hysteroscopy was, for operative hysteroscopy was OR hysteroscopy, where due to the fact that the hysteroscope had a rather large diameter, the cervix, the cervical canal, which is a narrow passage at the entrance of the uterus, had to be dilated prior to the procedure. But as the technology evolved, the diameter of the hysteroscope became smaller, and that allowed for outpatient treatment. Compared to OR hysteroscopy, in-office hysteroscopy, also known as outpatient hysteroscopy, has several benefits. Among those, the fact that small diameter causes less damage and no dilation is needed. There's a smaller risk factor related to the fact that no anesthesia is involved in the procedure. And nowadays, a major number of procedures can be performed by the means of outpatient hysteroscopy. But despite all the benefits, there are still some challenges remaining in this approach. And one of the main challenges is related to the fact that the endocervix, the cervical canal, is a rather narrow and curved passage that is very fragile. And since the patient is not having any anesthesia, the clinician should be extra thorough not to cause any kind of patient discomfort, not to say about some kind of tissue rupture. If we talk about VR training for hysteroscopy, a broad body of research has mainly focused on the OR hysteroscopy. We had some simulators available in the market, on the market as well, from Vertimed and from 3D systems, but to the best of our knowledge, none of them focused on this approach. So they completely exclude the passage of the cervical canal from their curriculum, not to say about vaginoscopy. And that's where we basically decided to apply ourselves. And I would like to present the first prototype of the platform that we developed. First, I will briefly talk about the scene generation. The model of the uterus, the geometry of the uterus, was created by the manual segmentation of a cryosection data set. Pardon me, that was... never mind, I forget the name, sorry. That's Helping Human, right? So there's an open source cryosection data set, and we use that together with manual segmentation to create mechanical model, as well as the visual and the collision models of our uterus. As for the mechanical parameters, we used a paper from Omari et al. To define the Young's modulus of the uterus, and we used some operative image data to create albedo textures, and then using automated tools, we also created normal mapping and height maps for parallax mapping. Now, a brief introduction to the hardware of the platform. We're using an Omega device to basically read the position of the hysteroscope and also render the force feedback coming from the virtual simulation. We also have a phantom of the vaginal canal and the vulva. And one important thing is that due to the fact that we want to have a fulcrum point that is not rigid compared to well, when we're outside of the uterus, but also have some elastic fulcrum properties when we're inside of the canal. We used a that provides such feature for us. And on the right side of the picture, you can see the hysteroscope with the forceps inserted in the working channel. There are two sensors that we use to track the position of the forceps and the grasping motion. From the software point of view, we use SOFA to basically simulate the physical part, the physics of our simulator, and we also implemented an API to connect it to the filament rendering engine. That's an engine developed at Google, and what we wanted to basically have is to map the visual instance to the physics server by the means of barycentric mapping. Here you can see a short demonstration of the platform. So the point of the exercise here is to, pardon me, to pass through the cervical canal and enter the uterine cavity. And once the trainee is inside of the cavity, he must collect all the checkpoints that are distributed inside the cavity itself. Of course, there are some trade-offs that we had to make for now. Mainly that is related to the fact that the cavity itself is already distended and the liquid distension is left out for future work for now. Yep. And another important trade-off that we had to make in the first version of the platform is the cervical canal itself, which has a rather mucus structure, and this part is not really implemented in this simulation, but that's a work in progress. I would like to show you a short clip showing how it actually should look like. So you can see that the opening of the cervix is more narrow compared to the first version of the platform. And here you can see the cervical canal with all these ripples and mucus-like structure. To validate or basically test the skill acquisition capabilities of the platform, we conducted a series of experiments involving 12 subjects. The aim of the exercise, as I said, was to introduce the hysteroscope into the cavity and collect all checkpoints with hysteroscopic forceps, which were rendered as 1 millimeter pink spheres. Trainees should have performed the exercise at the minimum time frame, but also maintaining the minimal force profile. And we assessed the performance of a trainee based on several metrics, including time-based metrics such as execution time, position-based metrics, mainly the length of the trajectory, and also a group of force-based metrics, mean force, cumulative force, and force fast for each transform. Well, essentially, the last one is related to the fact, well, we wanted to check if it actually provides any useful info regarding the tremor enhance or any kind of unparalleled motion. If we take a look at the results, and I beg your pardon, I just noticed that the title the subcaption of the box plot is not quite right. So the force FFT is actually the mean effective force, and the mean effective force is actually force FFT. So 4 out of 6 metrics proved to be valuable for us. Those are integral force, force FFT, trajectory length, and execution time, which showed a steady decreasing trend. And for 11 out of 12 participants, we actually observed improvements over 5 trials. But as you can see, the plateau effect is not quite clear here, so maybe even more number of trials would be necessary to actually check if a plateau effect appears. As for the future work, of course, we would like to have to work on clinical validation, and together with expert clinicians, we're conducting experiments to actually check if the platform can differentiate between experts and non-experts. And we would also like to work on the variability of the rendered scenarios and exercises. Namely, right now we're working on augmenting the simulation with complete vaginoscopy. And also we're working on the exercise for polyp removal. With that, I would like to conclude my presentation, and thanks all the clinicians that we've been working with. If you have any questions, I would be glad to answer them. Thank you.
Thanks a lot, Vlad, for the nice presentation. Is there any questions? So there have been, while you were actually presenting already, discussions about the haptics device that could be actually used. I guess from what Erik is saying is that you already chatted with him and indirectly mentioned maybe some haptics, or maybe in previous session, Vlad, did you already discuss, or?
Nope, not really. Nope.
Okay,
Visible
okay.
human, yeah. Thank you. I completely forgot the name. Of,
actually, you had it in the slide. That's why it was actually that was the reason why.
I guess I was just a bit too nervous.
Yeah, focus. You was just focused. So, thanks a lot for the nice presentation. I think we did not have actually a lot of. I don't remind actually, but I just prefer to say not a lot, because I don't remind myself about one hysteroscopy training. I don't know if there was others in some teams or companies. Do not hesitate to let us know. But yeah, that's quite an interesting work. But if there is any question, please unmute and post it in the chat. I'll ask one. You mentioned you showed that you had some mucus, surface. Is that taken into account in the mechanics, like all the I would say the surface? Can you really get stuck here, or
not really. We do not include the mucus structure in the pardon me, in the physical part of the simulation. So it's just the rendered for visual resemblance of the platform.
Okay.
Yeah.
Okay. And the second question I had, it was in your, and maybe it was on the slide, on one of the slides, but I might have missed it. It was if you are actually recording the forces applied to the different structures, and to set up some kind of score, or analysis of.
Yep. I think it would be better.
I might have missed it. Yeah.
Go all this way. Yeah, so basically what we do here is we record the force profile based on the force feedback generated by the device. And we use this data to calculate three types of metrics. The first one is mean effective force. That's mean force when the force profile is above some, let's say, what do you call it? Like above some passive state, when the clinician or a trainee does not move the hysteroscope or does not try to pass the canal. The second one is cumulative force, and that's the level of effective force multiplied by the time by dt. And the third one is pardon me. The third one is force fast Fourier transform. So what we do there is that's quite a novel approach, I would say, and we didn't really encounter it in any publications that I researched. What we basically do there is we take the FFT of the force profile, and we apply some low frequency filtering to get to get tremor in the frequencies between, if I'm not mistaken, between 3 hertz and 20 hertz, which correspond to either involuntary motion of hand or tremor, and we basically take the sum of these values of the real component, of course. Yeah.
Thanks a lot, Tom. Thanks a lot for. I got some other question, but time is running. Is there any other question from the audience? Do not hesitate to post it in the chat if you have some here right now, and otherwise, Vladimir will be in the first breakout room for this last session. I think we'll be able to move. I'll check the chat in the meantime and let you know, Vladimir, if anything is coming up. Otherwise, Peter, you can maybe come to the stage, and you should be able to share as well your own screen. Sorry, we had the sound test right before, so it's working, and just maybe the screen sharing test, and that will be perfect.
Yep, I just need to check which one is the right one. Perfect. So, is it working?
Perfect. Yeah, thanks a lot.
Cool. So, I guess, so today I'll quickly go over a tumor growth simulation using SOFA to simulate oxygen diffusion that a bachelor student of mine did a few months ago. And then also kind of a side thing, the SOFA Python viewing tool, and hopefully get some live demos of the example scripts, assuming everything works okay. So with that, so the motivation of this tumor growth actually is basically coming from trying to generate synthetic data for doing machine learning algorithms. So maybe some sort of Gaussian process inverse estimation of underlying tumor structures based on measurements from above. So the idea was to try and generate a bunch of fake data with some sort of realistic growth form of the tumor. But as you can see, or as you all I'm sure know, the different tumors have different structures. In our case, here in the project that I'm working on, we're looking at bladder cancer specifically, and so that actually grows quite differently in comparison to breast cancer or something that's more kind of blob-like. Bladder cancer actually tends to grow more like kind of looks like a cauliflower or broccoli inside the bladder. So the end goal is to achieve something like that. But to start with that, we just started with a basic growth simulation. So the simulation itself kind of assumes that we start with one cancerous cell that mutates from that. And a lot of this work was based off of another paper that, I should have a reference. If I don't, then in the paper that this work was published in, that hopefully will be published in the next few months or early next year, it'll be in there. But the idea is basically the cells can grow individually and slowly split, and then they are in different states for doing this growing and splitting based on the oxygen level. So normoxic, being normal state, can kind of move around a bit and just grow normally, and hypoxic means that it's usually not growing so much, but it tends to kind of move around a bit to try and explore its area a bit more. And then necrotic, basically dead. This part of the simulation was implemented in MATLAB, so this was purely implemented by my student. MATLAB was the programming kind of focus there, just from the background. But as maybe a lot of you know, like implementing three-dimensional diffusion algorithms, so for this sort of oxygen aspect, MATLAB is not always the easiest, and that's actually where SOFA kind of came in to be the savior, because it's so easy with these force fields to customize. And with the recent release of Python 3 and the force field can't think, well, anyway, the force fields in Python, it made it really easy to let the student prototype some things and test things in Python. And so basically the model that was actually done for the oxygen is simply just a normal diffusion plus an uptake term throughout the tissue volume. So essentially we're modeling sort of the difference in uptake from the cancerous cells from the surrounding normal cells is basically the idea. And that uptake is modeled with a Michaelis-Menten kinetic model, following again this general paper that we had. And then for the simulation, basically we fixed kind of a normal oxygen supply to one side of this cube mesh, and then placed a single cell in the MATLAB simulation in the center of the mesh, and then essentially had to talk between the two. So there was sort of a bouncing back and forth between a static state simulation of the SOFA diffusion and oxygen setup, and then the tumor growth. And that this is basically doable because of the different essentially update rates, or essentially the dynamics are quite different in a time domain. So the oxygen will settle out a lot quicker to a steady state solution before the cell would need to grow or split or anything like that. So it's basically an alternating between the two and using Python as the glue between everything. And then the simulation kept its speed by using Numba to actually implement the actual force field function that did the calculation. So there wasn't actually so noticeable of a drop between solving the SOFA force field with Python versus pure C++. So that was really nice. General results, this is from her thesis, basically ended up with, the oxygen diffusion level, as you can see here with the tumor. This is cut right in the center of that mesh block. You can't see the tumors because they weren't rendered within the Python model. But for an example, this diffusion plot would correspond to something like this example simulation here, where you can see the different states of the cells. So one thing we did run into was balancing this simulation such that the cells stayed balanced or kept alive. So that's, it was a first go at the simulation, and there's still tweaking to be done there. And then I think also moving this MATLAB fully to Python, or the entire thing to C++ in the future. But as it was a bachelor's thesis, it was kind of cut at this point. But essentially this will be published with the paper, and then the code will also be published online. And it's, like I said, pretty simple, just an addition. So with the normal diffusion within SOFA plus a different force field for this uptake to do that. And then I'll jump quickly into these view tools that were basically built side by side with that other work, basically to help the student view the simulation, and also help me and my colleague here in the office with throwing together new simulations in SOFA. So basically the idea is I've just put together a PyQt widget. So it's a regular Q widget or Qt widget that you can view a SOFA camera. And you can also add multiple cameras and different views. And with that, there's some built-in screenshot saving functions, depth information. So you could save a depth image, so make some synthetic RGBD. Recording videos, I'll try and show that really quickly. It's really easy. And it uses the automatically place the camera SOFA function. And then another nice thing is you can change the background color and the alpha value, which is really nice for papers or anything when you want a transparent background. It uses this view keyboard, and so you don't necessarily need to implement this directly, as I'll show. And then the Xbox controller hasn't been tested in a while, but as far as I know, it should work for controlling the view as well. But normally it uses just the mouse or the keyboard, and then the supporting packages. So there's two ways to use it. Basically like a normal Qt app that you would put together with Python. So I'm obviously not going to cover that here, but basically you can use it as a normal view or a normal widget, and then pass the root node and the camera reference that you want to use. and then some other parameters to basically set up the camera. And this internal refresh rate is so that you can actually move the camera view without needing to run the simulation. So essentially kind of like how Run Sofa works. Option 2 is actually a nice simple thing. So this is for somebody that really doesn't want to put an app together. And this is going to basically run a Qt thread in the background and run your main code on a different one. So you would basically define your main function. This would be whatever Python script you'd want, and then call or create your scene and then pass it to that function. And then it will jump into your Python script. And I'll show you really quickly how that's, or why that's really useful. I can't quite see my time, so I'm not quite sure where I'm at anymore. But
yeah, there is a bit more than a minute left, and that would be the 10 minutes. But again, 15 minutes are the total if you want to.
Yeah, I'll do it pretty quick. So basically, the idea is here's basically a regular setup your scene. I've wrapped it in a class just to help maintain reference to objects. But otherwise, you can directly define whatever keystrokes you want and things like that. And then, let's see, this one, I believe I was going to show the recording of a scene. So essentially, you have the regular stuff and the simulation's not running. But if we go ahead and I'll run this by just pressing spacebar, and then I'll start recording with pressing Shift-R. So it should be recording, and then I'll stop recording by pressing again. And then if we see here, this video should have just popped up. So that's one thing I did notice through all the forums, especially when I was starting, is how do I get screenshots? How do I do this? And basically now that with this Python 3 plugin, that should all be really easy and really nice. So as you can see, wrong thing. We now have a video. And then one more quick thing to the simple window. This is what maybe the general user might want to do that's not building a full app. So essentially create the scene, normal function to do so. And then you have essentially your main script that you want to do, what you're going to mess with, essentially. So in this case, you can actually do debugging, which is the really nice thing about moving to Python. It's a little quicker and easier to prototype. So I basically build my scene with my root node here, and then create this window, and then pass it this main function and the root node. And what happens there, if we debug this bad boy, you can essentially have a simultaneous non-locked GUI and then play with things and see what's going on in your script. So for example, if we wanted to change the background color, we could simply do so directly in the debugger, and we wouldn't lose anything there. So that was the main goal of this PyQt thing, is basically make everything super easy to try and just get started with simulations. And I think for the average user, at least from my experience, has been jumping into the Python, especially with the new plugin. So that's what, this whole thing is there to do, is to make it easier. So, with that, I guess I'm open to any questions or any other, I can also do my demos.
Thanks a lot, Peter. Yeah, maybe if you have some, if in the audience you want to see more about demos and so on, do not hesitate to ask Peter. As Guillaume just said in the chat, he seems to like danger making live demos during the presentation. So that's cool to see a live demo here in this symposium day. Yeah, if there is any question, please do not hesitate to come on stage and mute yourself. Again, as for any other presentation. My first remark is that first, it's super cool to see contributions as you are doing here, Peter, on your own. You seem to have built a SOFA MATLAB bridge. Is that correct? I mean,
so the
SOFA and MATLAB through Python, right?
Yeah. So essentially, you can call the MATLAB engine from Python, and then just wrap that in a Qt widget, and then basically send signals when one was done to activate the other one, and then pass back and forth. So that way a GUI could stay alive at the same time. But I don't actually have that simulation on my computer at the moment. Yeah.
Okay. Just I was thinking that kind of like bridge is also it could be also of interest. Yeah, even if it's a basic bridge between MATLAB and SOFA, is could be definitely super interesting to anyone. I know that there have been already people doing that, but having for instance, in SOFA Python 3 plugin, an example of that, even as simple as possible, it would be very nice.
Yep. Like I said, that should be published, early spring, something like that. I'll open the code.
Cool.
Yeah.
Perfect. That would be very nice. And another remark. So yeah, that would be. We have other people actually working on cell simulation. So that's it's reminding me several things in seeing what you've done. Maybe one question.
Mm-hmm.
You're having diffusion here on the tetrahedral mesh. Is that correct?
Correct. Yeah.
Okay. And what you call uptake term, right?
Mm-hmm.
That's this part you implemented in SOFA Python 3. Is that correct?
Correct. Yep. We subclassed the 1D force field and then. Yeah.
Okay. And the so-called forces, or the uptake effect, is a nodal information that you compute, because I guess you cannot really reintegrate over space in all tetra and so on. Basically, implement a FE-based integration, or can you?
Yeah, no, we basically implemented it as sort of like, I guess you could kind of see it as like damping, essentially sucking energy out of the system, or slowly dragging the positional states down, and then we had a zero cutoff, so some constraints. I forget what the stopper constraint in SOFA for all the nodes to make sure they didn't drop below zero, and then MATLAB would calculate essentially what the tetrahedron coefficients needed to be for the uptake, and then pass that back to SOFA Python, and then we would update the internal uptake, or essentially diffusion coefficients, you could think of it as, and then rerun the simulation from the last one as a warm start.
Cool.
And then just run until convergence, basically.
Maybe one last, and it will be a comment rather. If there is a question in the audience, I'm speaking more and more, so do not hesitate to just interrupt and ask yourself the questions. So I'm going to wait a few seconds if there is any question. And yeah, Eligius, yeah.
Yes, do you need any kind of remeshing in your calculations?
Sorry, didn't quite catch that.
Any kind of remeshing in your calculations?
Remeshing? No. There's just a static mesh. So actually the tetrahedron size is also pretty effective for like the number of cells that end up being per tetrahedron. So, that's pretty elementary implemented, I would say.
Okay, great, thank you.
Thanks, Eligius. If you have other questions, Eligius, and maybe you would have some, but do not hesitate to join Peter in the room 2 in just 15 minutes, right after the last and not the least presentation. It will be Zara that will be presenting her work about the hybrid methods for realistic soft tissue deformation. Thanks again, Peter, for submitting an abstract, for submitting a candidate for the award of the symposium, and let's see each other right after for the breakout rooms. Zara, you should be able to come up on stage here and sharing your screen as scheduled. Yeah, perfectly. We can hear you. It's already a first step.
Okay.
All right, screen sharing starts. Perfect, and I think you can go full screen, and we should be able to see your screen.
Great. Can you see the?
Yeah, that's fine. Yeah.
Okay, thank you.
Perfect.
Okay. Hello everyone. I'm going to present a hybrid method for fast realistic soft tissue modeling. The aim of this modeling is its use in surgery training simulators. So in these simulators, it's so important that the simulation run at interactive rates, while their accuracy of the deformation is not of high importance, but the model should be realistic. For a realistic soft tissue modeling, it should be high resolution and it should contain enough details. Physically based simulation is a great choice for this purpose, because it's very accurate, especially in high resolutions, but its speed decreases as the resolution increases. Another advantage of this method is that it's very useful in novel conditions. The alternative is the data-driven simulation, which is accurate and fast in comparison with physically based simulation. However, it's almost impractical in encountering new conditions. To take advantage of the advantage and its of physically based simulation and data-driven simulation, and make a trade-off between its advantage and disadvantage, hybrid methods are introduced, which use a combination of data-driven and physically based modeling. We use the hybrid model by enriching an interactive coarse finite element model by data-driven simulation. So for this purpose, we consider a finite element model, which is coarse, as XC, and we try to find an enriching function to find a high resolution model XF. So here our work is to find a very good approximation for function F, which we use data-driven simulation for this purpose. So to provide a data-driven simulation, we need a conforming coarse and fine deformation models in the database. So as a pre-processing stage, we extract features from the coarse simulations, and we use the information of the coarse and fine models in the database to train a regressor. At the runtime, we simulate the coarse model, which is fast, and we extract its informations and compare them with the features of the coarse models in a database. By this comparison, we find an interpolation base for linearly combining the fine models in the database and for finally approximating the fine model at the runtime. So here are the steps. We should have a proper pre-processing stage to provide conforming coarse fine pairs, and we should have different physical and visual models, especially because we need to enrich the coarse model with the high resolution informations. The next step is feature extraction. Can use the information of the node positions and information of the normals to create feature vector theta with a dimension of L. So our aim is to decrease the time complexity of this stage. For this, we use a feature selection approach. Here we can use machine learning techniques to decrease the dimensionality of the feature vector. However, we took another approach. By considering that the deformation around the contact node, the node that the force is applied, is more distinctive in comparison with the deformation around for the nodes which is far from the contact node, we can define a neighborhood, and we can just extract the features from these neighborhood nodes. This helps to decrease the dimensionality of the feature vector. Another advantage of this approach is that we disentangle the deformation pattern from the node position. This helps us to use this deformation for smooth enough models as the deformation that happens on the nodes that are close to this node. So we can decrease the number of deformations that we need in the database. This also decreases the time complexity of the procedure. For the regression, we consider the matrix of coarse feature vectors as theta and the matrix of fine feature vectors as x. So the xt at runtime, the fine estimation, is obtained by multiplication of x to the psi, which is the interpolation matrix, and w, which is the wave vector. So this is similar to the linear regression. However, because we want to simulate the nonlinear deformations, instead of inner product, we take advantage of the kernel concept. So we compute Vij by this kernel formula. And the psi would be this matrix. So here, since the psi, we need to inverse this psi matrix. This doesn't ensure that we have always positive waves. These negative waves can cause artifacts in the final deformation. So we use a non-negative least squares approach to avoid negative waves, and so avoid the artifacts due to these negative waves. For the implementation, we consider the mesh resolution as this, and we consider different coarse and fine volumetric and surfacic models. And we also consider the fine and coarse visual deformations, the same as the fine surface deformation models. Our assumptions is that the soft tissue is elastic, homogeneous, and isotropic. And by this assumption, we create a database containing 200 conforming deformations, which you can see some of the samples here. For the implementation, we use SOFA framework, especially for major parts of our simulation. It helps it provides tools for FEM-based simulation, conforming.
I lost the sound here. I don't know if I'm the only one.
Yeah.
Okay. Zara, we cannot hear you anymore. Ah, yeah, you're back.
Ah, okay. You can hear me?
Oh, yeah, you're back. Yeah, you're back. Yeah.
Should I start from here?
Yeah, it's fine.
Go back.
Yeah. Okay. No, the result slide.
Yes. To examine the algorithm performance, we apply a 10-fold cross-validation experiment, and we compute the interpolation error as a root mean squared error by comparing the approximated fine models with the original fine models obtained by FEM. Here you can see the RMSE based on considering different number of features, 10, 50, 100, and all features. For a varying kernel width parameter sigma. I'm not sure if you can see here. Can I with this?
Yeah, we have the same. Yeah, perfect. There we see what you see. Yeah.
Okay. To examine the time complexity based on the number of deformation samples K and the number of features L, we can see that, for example, the time complexity for computing W, the waves, is that the time complexity is linearly dependent to the number of features and the number of samples. And you can see the time complexity also for the other matrices. So here we compute the deformation for the 5 deformation, and we computed.
We're losing you again, Zara, and we're close to the end of the time. So yeah, but it's
yes,
yeah.
Yes.
I think you're back. Yeah.
Okay. And our model, our fine hybrid model, you can see that our model is running so fast. nearly interactive. So as a summary and future work, as a summary, we can say that we modeled a high-resolution simulation by enriching a fast FEM. The coarse FEM runs around 0.6 seconds, and the data-driven enrichment stage took around 0.01 second, which is real time. For future work, it's very helpful if we increase the conformity between the coarse and fine models in the database, for example, by using model order reduction approach. Also, there is one important thing that we should consider in data-driven simulations. In these simulations, even if one node has a huge error, it can dramatically change the shape of the model. So we should. It's very good if we use post-processing procedures to provide smooth deformations. Thank you for your attention, and I'm here for the questions.
Thanks a lot, Zara. So as you noticed, so as you heard, sorry, there was some sound issues. I hope everyone got it as good as possible. Is there any question in the audience regarding our last presentation of the day from Zara in the audience? Yeah, please go ahead, Eligius.
Can you change the initial shape of for the screwed models, these coarse models, to have to interact later with the fine model in the course of your of the analysis?
Oh, excuse me. I didn't hear the first part of your question.
When you start your simulation with crude models, the coarse, okay, the coarse models, and you go on, and can you change? Can you change the coarse model, which is the basic one, to change somehow, basing on that's what you will get from the fine model, which is made from time to time only. Can you correct the crude model somehow?
Okay. You're asking that if I can change the resolution of the coarse model. Is this your question?
Yes, but not only the resolution, but general shape somehow.
You mean not the liver, for example? Yes?
So, excuse me, can you say again?
You mean...
that's what you said, just if you can repeat, because...
you mean for another, for example, geometrical model?
Yes, but based on this coarse model with which you start. Something like in shape sensitivity.
I just used one model, this shape that I used. But if we contain enough models, enough different geometrical models, yes, we can use the informations for another. However, it's important that the informations of the material doesn't change, because we didn't consider it in our simulation. For example, I just considered the Young modulus 0.445, for example.
And for the dimension.
We'll maybe keep some questions for the breakout room so that we can split. If it's okay for you, just keep your question nicely warm, and we'll create 3 breakout rooms. The first one will be for Vlad, the second one will be for Peter, and the third one will be for Zara. we'll make instead of 20 minutes because there have been 3 presentations here. We're gonna make like 3 times 5 minutes, so 15 minutes. Let's split in the rooms and carry on asking the question, and we're gonna have the ending of the day with the award ceremony right after. So see you in 15 minutes, and have a good breakout room session.